Good morning, everyone. Thank you for the good wishes. I'm doing well. Thank you. A confirmation about the audio, please. If the audio is clear and available, thank you. We shall be starting in a couple of moments. I'm doing fine. Thank you. Much better. Yesterday, we did not have a session, Dikshit, because of certain health issues. I could not carry out the classes yesterday. We'll accommodate it with an extra session, maybe on a Saturday, on this coming Saturday or some other Saturday. You got a much needed holiday as well, right? True. Monthly magazine, Sulakshana, just pick up one by one uh, from the month of May or June 2023. One by one, you can pick up those magazines and you can straight away go ahead and start learning and getting yourself familiarized with the various different current affairs aspects. And just ensure that every monthly magazine that you read, you manage to revise it within 1 week. Otherwise, it won't be worth anything at all. So please do revise it as soon as possible. No, May or June 2023 would also do. Okay. So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography, where today we shall be proceeding ahead with the portions of the movement of the plates and other aspects of geomorphology, where we had left the discussion in the last week. So, last week we discussed about the interior of the planet, we discussed about the internal structure of the planet, and we also discussed about the aspect of the continental drift theory. Now, when we talk about the continental drift theory, which was provided by Alfred Wagner, we talked about the aspect, or we looked into the fact that how Alfred Wagner was able to basically talk about the present day movement of the continents and the oceans and the present day position of the continents and oceans based upon the fact that he had studied various different evidences which all pointed to the reality that long time back all the continents would have been together and basically they have moved away from each other. Alfred Wagner was very convinced that the continents are moving with respect to each other. And for that, he used the various different evidences to support his claim. But then, not only that claim would suffice. In order to postulate a theory, you also need to be able to provide a reason. Why do you think that the continents are moving with respect to each other? And it is in that reasoning where Alfred Wagner was found to be falling short. And the continental drift theory, thereby provided by him, was found to be falling short. In the sense that the reasons that were cited by Alfred Wagner were basically very limited, in the sense that he said that the continental land masses, they were so very light that they would be floating over the oceans, and thereby they would be held up by the gravitational pull of the moon and the sun, and also a combined effect of the force of buoyancy which would keep the continents afloat and centrifugal force. All these events and all these forces, they are responsible for the drift of the continents. It was later found out that none of those reasons or assumptions made by Alfred Wagner were even close to being correct. And because of that, because of lack of understanding of what were the mechanisms which drove the continents away from each other or towards each other, because of that, the theory of continental drift was rejected. Now, this was a unique case, by the way, when almost everybody was convinced that yes, the evidences point in the same direction, but because of the lack of proper mechanism which could govern or which could form a principle that why the continents are moving, or in what principle are they moving in a certain direction only, or will they continue to move in a certain direction? So because of lack of that, this was rejected. Now, in the meanwhile, from the 1920s all the way till the 1960s, you had other different researches and theories which were made and which were carried out in the process in the time duration. And eventually, all of these various theories, some aspect from continental drift, some aspect from convection current theory, some aspect from seafloor spreading theory, all of them were then later on amalgamated and utilized in order to postulate, in order to prove the continental drift and basically formulate the plate tectonic theory. So, all the theories that we are going to read about, all of them have played their own significant role in postulating the plate tectonic theory about the movement of the plates, the continents, and the oceans. How do they happen? Why do they happen? All of that is basically clearly demarcated by the plate tectonic theory. So, all the meanwhile, all the other theories that you see, they are simply a performing act in support of the plate tectonic. So, we have taken a look at the continental drift theory. Today, we are going to take a look into convection current, seafloor spreading, and eventually that will lead us into plate tectonic theory. Once we understand the basics of plate tectonic theory, how the mechanism of it works, what is it exactly about, then we shall be implementing it to understand that how is it that Indian plate moved and how is it that the formation of Himalayas was actually observed. Why is it the case that the height of the Himalayas is still ever so increasing? Why is it the case that the region of Himalayas, they are frequented by massive earthquakes? Earthquakes happening in Nepal, Uttarakhand, northern portion of India, northeastern portion of India, northwestern portion of India. Why is it that that region is so very frequented by earthquakes? That is something we are going to look into. And also, we are going to look into that what does the future look like? In the sense that what does 100 million years down the line, what will be the shape of the continents and oceans as we look at it? We do know that the continents, they are moving, but then in which direction are they moving? And what are the evidences on the ground to tell us that around 100 to 200 million years down the line, you might have the creation of another Pangea like supercontinent? Remember, last Friday, at the end of the session, we also talked about the fact that the formation of Pangea, the breaking of Pangea into Laurasia in the north and Gondwana land in the south, and then further breaking them into different types of continents. Now, this is a part of a cyclical process. Every few years, the planet Earth basically observes this. That is, excuse me, every few years, planet Earth basically experiences all the land masses coming together and then all the land masses moving away from each other. So, all those details we are going to take a look into. So, here, let us start with the convection current theory. Recently, Japan got a new island due to volcanic activities under the ocean. Can it be asked in mains? See, understand. I understand that many portions of current affairs, whenever you read it for the first time, immediately you get a kind of a query in your mind that can this be asked in the mains? Can this be asked in the prelims? That is why always advisable to have a preview of the PYQs and also try to think about it from the point of view of the examiner. If let's suppose you had to frame a question about it, that a new island is created near Japan, how would you have framed the question? Right? So, in many of the cases, you will find that you won't be able to frame a question from that. For example, many of you had written to me and asked me that earthquakes in Nepal, is it going to be asked in the mains exam? So think about it. What will UPSC frame as a question? Why did the earthquake occur in Nepal in the month of October and November 2023? Is that a question that UPSC will ask? Or can UPSC ask such kind of question? Obviously not. So think about it, that whether a question can be framed from this topic or not. While you are saying about the portion of the creation of a new island, UPSC can ask you about the fundamentals of it. That how do islands get created? That can be asked. But why an island is created underneath the or near the region of Japan? That is a question that UPSC won't be pinpointing itself to. Okay. Now, the drawbacks of continental drift theory we have talked about, Chandu. If you recall the last week's discussion, we did talk about the drawbacks of continental drift theory, in the sense that when we talk about the drift theory, it does not, or basically the reason that it postulates about the movement of the continents over the ocean, that is not how it moves. When it talks about the westward drift of the continents, it purely ascribes it to the gravitational pull of the moon and the sun, and the gravitational pull of the moon and the sun is nowhere as strong. Now, continental drift theory even talks about the fact that as the continents have been drifting west, there have been formation of mountains in the region of the Rockies and the Andes. But then again, it contravenes the basic understanding of the continental drift theory, that when the continents are freely floating, how is it that the mountains get created? So these are few of the drawbacks. Okay. It has been discussed in the session, Chandu. It has been discussed in the class. Okay. So now we come to the portion of the convection current theory. This convection current theory was provided by Sir Arthur Holmes, or simply Arthur Holmes also would do. Okay. Now he talked about the presence of a convection current in the region of the mantle. Now here, before looking at what is it that he actually talked about, when we talk about convection current, what is a convection current? So, convection current is basically one of the modes of transfer of heat. Okay, so imagine an experiment. We will revisit this experiment time and time again. So imagine a kind of a larger utensil that you have at your house. Let's suppose you are boiling water on top in that utensil. Now, all of you at some point of time in your life or the other would have boiled some amount of water on yourself, or at least you would have seen someone boiling water. So I'm sure you would be very familiar with the mechanism involved. So let's suppose this is the flame on which you have kept this utensil, where there is a pan full or a utensil full of water. Now, if you would have noticed, now what happens immediately? When you start heating water, is it the case that immediately it will start forming bubbles on top? No. Is it the case that the top portion will start boiling immediately? Absolutely not. So, what actually happens? If you notice it carefully, when you heat that water, initially you will find the presence and the formation of bubbles at the bottom of the utensil. You'll find the formation of bubbles at the bottom of the utensils. Why? Because at the bottom of the utensil, the water gets heated up with significant amount of speed, because it is in contact with the fire, with the source of heat. So water will get heated up, it will form those bubbles. Now these bubbles, they will rise up and they will be heating the regions above. Now as they heat the regions above, the colder water in these areas, they would basically sink and they would replace the water which has risen up. Now, this process continues, and after some time, you will come across a situation where that heat has been transferred in a way that the water in the entirety of the pot or the utensil starts to boil up, starts to heat up. So, what you observe as the mode or the method for the transfer of heat is actually the process of convection. You would have read in your childhood days about the method of heat transfer: conduction, convection, radiation, etc., where convection is that method of heat transfer where the particles, they end up moving from one region to another, carrying heat energy from one region to another. So that is something you would have observed quite significantly. So that convection is one of the methods of transfer of heat. We know that about convection. Okay, so that is the basic about convection, and this was utilized by Arthur Holmes to suggest that something very similar is at play even in the interior of the planet in the region of the mantle. So convection basically method of heat transfer by the movement of particles. Okay. So here, basically, when we say movement of particles, the warmer objects material rises up and colder substances sink to replace it. So this process continues. Now, I'm sure many of you would have seen the boiling of water till now endless number of times, but you would have never observed it. So today, kindly do observe it, that when you heat that water, how does it behave? It is basically the bubbles form at the bottom, which rise up, heat the upper portions, and that continues. Why the bubbles get created at the bottom? That is where the temperature is attained very quickly because of being in contact with the heat source. So that is why as the water temperature increases, water gets converted into steam. And that steam basically is gaseous. So that is why you will find gaseous bubbles at the bottom of that container. Now, having said that, what is it that Arthur Holmes proposed? Arthur Holmes basically said that look, in the interior of mantle, you have various different materials which are radioactive in nature, and also you have significant amount of residual heat which is provided from the interior of the planet also. Remember, we had talked about residual heat at the time of formation of planet. We had talked about the fact that how there is in presence, there is in existence the residual heat ever since the time of formation of the planet. A lot of heat has been retained in the interior, in the central portion of the planet, and that heat is referred to as the residual heat. We had talked about it, right? So that residual heat, along with the radioactive materials which are present in the region of the mantle, both of them, they are able to generate a kind of a convection current in the region of the mantle, which helps transfer heat. So how would it happen? So basically, you have, let's suppose, the region of the crust, which is going to be thin, not very thick, and then the region of mantle. Okay, so he said the presence of radioactive materials and the presence of the residual heat basically generates a convection current which is present in the region of the mantle. Now, convection current basically involves movement of particles, right? Convection is basically that mode of transfer of heat where the particles, they have to move. We have seen earlier in the case of water that how the particles, they are moving up, where the hotter particles, they rise up, the colder ones, they settle down at the bottom, right? Now, when mantle is in a solid state, how come can it have the presence of a convection current given that the mantle is in solid state? So basically, that is what was explained by Arthur Holmes when he said that look, you have the provision of both residual heat, which is being provided from the region of Gutenberg discontinuity, residual heat. But that residual heat will be supplied from where? Is it something that will be supplied uniformly all across the region of the outer core and all across the region of the mantle? Will it be supplied uniformly? No. That is not the case of heat dissipation. That is not the case of heat present in the region of the interior of the planet as well. So basically, from certain concentrated areas across the entirety of planet Earth, certain concentrated areas, from there, that residual heat is generated. And that is where you have the presence of this mantle convection. It is not going to be uniform across the entirety of the interior of the planet, but rather concentrated. It might be possible, let's suppose, that in this area, residual heat is being provided and it continues to be provided for, let's say, 50 million years, 100 million years. A convection current is generated there, but in the rest areas, it might not be present. And it might be the case that after 100 million years, even this portion of that residual heat is not present anymore. So that is the case where the presence of radioactive materials at the depth in the mantle and the residual heat present in the interior of the planet Earth, that generates that enough heat where in the portion of mantle, the materials they get heated up. The materials they get heated up extraordinarily, they melt in certain areas. Let's suppose there's a lot of heat which is provided in this portion. So in this immediate vicinity, the materials would be melting. Now, these molten materials, because they would be lighter, these molten materials would rise up. Now, as they would rise up, eventually, it would carry the heat somewhere here, right? In the meanwhile, you have the colder solid mantle, comparatively colder solid mantle, which is present in the surroundings. Okay. Now, this colder solid mantle, it will immediately try to sink and replace the materials which have risen up. So, in a way, you have generation of a convection current in the interior of the mantle. Now, this convection current transfers heat from the interior to the outside. Now, when we talk about this convection current, what will be the impact on the ground surface if indeed there is an existence of a convection current like this, carrying excess heat from the interior of the planet to the exterior? What will be the impact? So, there also, if you break this furthermore, residual heat, guys, we had discussed that it is the heat which is trapped in the interior of the planet ever since the time of the formation of planet. So as the planet was getting created, we have seen that it started cooling down from outside, whereas the inside continued to remain hot. So that heat which had been retained, that is residual heat. Okay, so Chandrajyoti, I hope now you get the correct answer. And Bhavna, I hope you also now get the answer. Okay. So here, why is it and how is it that the convection current is generated? Again, Bisujit, please listen to this carefully. So the region of the mantle which would get heated quite significantly, that would get molten. And that molten material would start to rise up because it would be lighter than the surrounding. It would rise up. Now, as those molten materials would rise up, now that would create a vacancy from the position where they have risen up. There would be a gap created. Now that gap would be fulfilled and immediately filled by the nearby colder objects in the mantle which are present. That gap would immediately be filled over. So in a way, if let's suppose the colder solid portion of the mantle replaces this, now there would be something to replace the other ones also. So you have a complete convection where the molten materials, they induce a motion, and that motion is then fulfilled by rest of the portion of the mantle. Now, what is the impact of that created on the ground surface? Now here, if you consider that entirety of convection current will have a vertical arm and a horizontal arm as well. What do we mean by that? So a convection current would appear to be somewhat like this. Mantle is not in a molten state, my dear friend. Mantle is not in a molten state. Please take a revision of that. So this is the portion of the convection current. So this is the vertical component of the convection current, and these are the horizontal components of the convection current. So when you have the vertical component of the convection current heating up the surface, now immediately what happens is that the surface, it rises up, it starts bubbling over, just like when you heat any material for a prolonged time, any kind of a solid, you will observe the thinner solid, which is not very thick, thin and lighter solid. If you heat it up, you'll find some kind of bubbles getting created on top of it, flaky substances getting created. It gets weaker and thinner because of the heat. And then it might even lead to a volcanic eruption sometimes if the crust is not strong enough. These molten materials, when they come and hit the closer to the surface, if the crust is weaker, that might even lead to the eruption of volcanoes in certain unique cases. But then you also have the horizontal component of this convection current. And the horizontal component, think about it, you have that heat component in the interior which is moving away from each other. So as that horizontal component of that convection current comes into play, it can basically move the land masses away from each other. It can move the land masses apart from each other, right? Then you also have a sinking portion of the convection current where the materials which are colder, they will start to sink down. So there, wherever you have the mantle which is sinking or substances in the mantle which are sinking, so naturally, there will be a kind of a pull on the surface also. So a surface which might appear to be very plain and featureless, if you have a sinking portion of the convection current there, it might be possible that this portion experiences a kind of a depression. So basically, Arthur Holmes said that you have the presence of convection current in the region of the mantle. That convection current is generated because of the radioactive materials present in the interior of the mantle, and also because of the heat provided from the region of outer core sometimes. So that heat generates that convection current, where the portion of the mantle starts to melt, it rises up, and in the meanwhile, the colder portions or colder particles of the mantle, they sink to the bottom and they replace the vacancy created. Now, in the process of this convection current, you will feel the impact created on the ground surface, where the vertical component of that convection current will heat up the land surface, create weakness in that land surface, create cracks and fractures on the land surface, whereas the horizontal component has the potential to pull the lands apart from each other, pull the crust away from each other, and then you have a sinking vertical component as well. So that was what was surmised by the convection current theory. Now, while Arthur Holmes did not concern himself with the fact that why is it that indeed North America did it move to the west, South America did it move to the west, he did not concern himself with these details. But then he talked about it that this can be the impact on the land surface. So he did not get entangled with the convection with the continental drift theory. But then his theory, that is the convection current theory, did provide a reasoning why the continents can actually drift away from each other, in a way, if you think about it. Okay, so here, presence of presence of convection current in the interior of mantle due to presence of radioactive materials and heat provided from core. What this does, it melts the portion of mantle which becomes lighter. It rises up while colder solid mantle replaces the vacancy created by rising materials. Okay. Now, this convection current can lead to changes on the surface. Okay. So, that is basically the case about it. Right. Is it possible to move the continents which are very heavy, which are nearly 30 to 35-kilometer thickness by this convection current? Absolutely, yes. Absolutely, yes. Is convection current responsible for creation of asthenosphere? No. Asthenosphere, you have the presence of, in asthenosphere also you can have a different convection current, but no, it is not responsible for the creation of asthenosphere. Is this radioactive material present in a particular area or across the mantle? So it is spread over. I hope when you think about, when you imagine the interior of the planet, I hope you are not imagining it like how you create a cake, that every layer will be very similar, every material will be equally distributed. I hope that is not the case, that in your understanding. If you have an improper understanding about the interior, just to throw light on it, when we talk about, let's suppose, the portion of interior, you will have, as we talked about the region of the outer core also, while we're talking about the geomagnetism, concept of geomagnetism, that it is not as if all the materials are equally distributed in all different areas. No, you will have certain materials which have a concentration maybe in certain area. Now that is also not always fixed, that under the region of Africa, if there is presence of certain radioactive materials, it is present only in under Africa, it is not present anywhere else. So that is not the case. You might find certain chunk of radioactive material somewhere or the other. Now, another doubt that I am seeing, which is repeated very frequently, is that what is this residual heat? Many of you are getting confused in that residual heat, and whether that residual heat is being supplied in a continuous manner. So, residual heat is the heat which is present, which has been present and trapped in the interior of the planet ever since the time of its creation. Ever since the time of its formation, we have talked about it, that while the external part of the planet started cooling down, the internal part continued to remain hotter. And it is in that internal part where the temperature was significantly higher. So that was the residual heat. Now, that residual heat, it is not as if because there is heat, so from everywhere, the same amount of heat will be supplied in the portion of the mantle. No, it might be possible that from now that heat is trapped in the interior in the form of materials and their energy that is present. That is how that heat is trapped. So time and time again, that is when we say time and time again, we here are referring to maybe for a duration of 50 million years or 100 million years. Time and time again, you will have these that heat being suddenly supplied to the region of the mantle at the region of Gutenberg discontinuity. And that is where the process of melting can be initiated for the portion of the mantle. Now, it might be possible that under the region of, let's suppose, Hawaiian Islands, you have that heat, residual heat continuously being provided. Under the region of Reunion Islands, you might have that residual heat continuously being provided. So it changes its position also. But nonetheless, whenever periodically that heat is being provided, it will melt the portion of the mantle and it will create that convection current. Okay, right? Now, uh, okay. So this process can break the continent, Surya, yes. And is it the reason for volcanic hotspot? One of the reasons, yes, Rohit. Uh, Sandeep, I am very new innocent student. Please tell about answer writing. So innocently, first of all, listen to the content. Once you have understood the content, answer writing will follow. Shallow in astronosphere, this convection current found, which you have drawn, are they touching the crust? Please clarify. Yes, they are touching the crust. Um, Class has been started at 6 a.m. Dot 6 a.m. Bhavna, how convection current, Shyam, that is what I have been talking about. So, okay, please, again, I I never thought I will have to clarify it in every class, but understand this is since many of you are attending the session for the first time. Listen to one thing very carefully. Many of you have seen you are typing the questions quite continuously and you are so engrossed in typing your own question. You forget and ignore the discussion which is going on because you are so very obviously that happens when you are typing. Not many of us are good with multitasking. So, in the meanwhile, when I explain something, pay attention to that. After that, ask your questions. So, Shyam, while you were asking the same question continuously about whether the continents can move by the convection current, we have explained the fact that why there is a convection current in the portion of the mantle. And if others share the same question, listen to the solution very carefully. I'm not going to repeat it. I've already repeated it 10 times now. In the portion of the mantle, wherever, let's suppose, you have sporadic presence or sudden presence of heat, sudden generation of heat, why will the heat get generated? The heat will get generated either because of the presence of radioactive materials in certain areas which undergo thermonuclear reaction, such as uranium, such as isotopes of certain materials, certain elements which are present, they can initiate a thermonuclear reaction. And when that thermonuclear reaction is initiated, then that will produce so much heat that in the region of that portion of mantle, materials will melt. Now, once the materials have melted here, molten materials are going to be lighter than the solid. So, molten materials are going to rise up. As the molten materials, they will rise up virtually, they will basically have a convection current in place because as they have risen up, they have created a vacancy from the portion where they have risen up. So you will have colder materials from the surrounding region that will replace them. So, as these molten materials they rise up, there is, as they keep on moving up, they will start melting the materials in contact, and eventually you will have the colder materials which will replace them, and the convection current is completed. Okay. Uh, Relationship between oceans and convection current. Are we able to understand this? The relationship between earthquake and this, relationship between volcanoes and this, that is a different matter altogether. This is a theory which was provided immediately after continental drift, and this is a theory which talked about the heat transfer from the interior of the planet to the exterior, because till now there was no concept which was in place which could talk about that how in the interior of the planet, if there is so much amount of heat, whether that heat is continuously trapped or whether that heat is being released from some region or the other. So that was explained ably well by the convection current theory. Okay. Now, after this, Satyam, again the same question. Okay. Am I not audible when I am trying to say that why there will be a convection current in the mantle when mantle is solid? Is that portion understood or is that portion not understood? Is it something that is simply bouncing above the head? What is the problem with that? Is that understood? Anybody who has not understood that? Understood. Just repeat it once. Okay. And after that, again, I will repeat it once. I will do one thing, something which will satisfy the inner thirst for many of you. And that is the way the education system has been framed. So I don't put the fault on you. But basically, let me write it down so that once you also get an idea that, okay, this is going to be available in the PDF, immediately all that query will go away. So, why convection in the mantle when mantle is solid? In mantle, despite mantle being solid. Is that the question? I think that is the question. That is, yes, the time for doubt taking is very long. Yes, I agree. I could not agree more. So why there is convection in the mantle? When mantle is solid, why there is convection in the mantle? So suppose this is the portion of your crust, this is the portion of your mantle. Let's suppose in a particular area, let's suppose in a particular region, there is production of heat. There is generation of heat. Now generation of heat, let's suppose, can happen here. Or let's suppose it happens somewhere here because of radioactive materials, or it can happen here also, let's suppose. Now, if there is heat which is generated here because of the presence of certain concentration of radioactive materials, or the residual heat which is provided from the interior of the planet, from the region of the outer core, now this portion will melt because of the heat. So portion of the mantle where there is heat, portion of mantle which experiences heat, starts to melt. So, as a consequence of that, molten materials being lighter rises up and is replaced by the colder solid from the surroundings. The colder solids also get heated up melt and rise up. The gap is filled by nearby solid materials. Right? So I can keep on repeating this if you want, but then the process is repeated to generate a convection current. Okay? That is the case of the convection current theory. Dikshit, my dear friend, the problem is till now we have not even started the complicated portions of geography. So if you think about these portions as a complicated, then basically you are in for a lot of treat coming ahead. So These are one of the easier things. Okay. I hope this is understood. Yes, Ziva, these are written in the 11th NCRTs, basic NCRTs. Now we come to the portion of the seafloor spreading. Now, this was another theory which was basically provided after the Second World War, and this was basically provided by Harry Hess. Now, there basically our understanding about the oceans of the world has never been very great because mankind would always observe the oceans from top. They would think about the water to be plain and featureless, and they would always extrapolate it to the fact that even the ocean bottom would be very similar, plain and featureless. Now, that process continued. And we did not have enough scientific instruments to discover about the portions in the underwater in the region of the oceans. We did not have enough instruments to do that. But then World War II came. Now, during World War II, the Germans developed a weaponry which the Western powers had never thought about. So obviously, they could never think about how to defeat that weaponry. And that weaponry were the German U boats or the German submarines. Now, these German U boats or the German submarines, basically, they could lurk underwater. They could remain underwater. This was for the first time that a submarine would be deployed in warfare during the Second World War. So they would lurk underwater. Suddenly, they would surface and attack the vessels of British troops or the American troops, and they would cause a lot of damage and destruction. So immediately, everybody realized that these U boats need to be destroyed in order to have the naval deployment by the Western forces and the Western powers. Now, what they developed was basically the underwater radar of sorts, sonar, the sonar equipments that you have, where they map out the ocean bottom, etc. So that was discovered. That was attached to the base of the ships, and the ships would sail across the region of the Atlantic, across the region of the Pacific, and they would be scouting for these submarines, and in the process, they would also carry out the reading of the ocean bottom. Now, you had one of the naval expeditioners in the US Navy with the name of Harry Hess. Now, Harry Hess, initially, when he was deployed over the region of the Atlantic, he would ensure that basically he would carry out the readings of the ocean floor in order to detect whether there is a German submarine lurking around or not. But then, in the region of the Pacific, where there was no such issue of German submarine, there also, Harry Hess would continuously switch on the equipment or the machine and carry out the readings of the ocean bottom. World War II ended. The submarines and the threat of the submarines, they did end. But then these machineries, they did remain. The equipments continue to remain. And with the help of the readings generated by the equipments, Harry has made a series of very substantial observations. Now, the observations made by Harry Hess, if you will observe, he said, or he basically observed or noticed, that oceans are not featureless plains, as mankind had always thought. Oceans are full of very different kind of landforms underwater. Just like on the land surface, you have mountains, you have valleys, you have plains, you have plateaus. Something very similar is to be found underwater in the ocean also, where you have mid oceanic ridges, rise, trenches, etc. Different types of features under the ocean. He also observed that when you calculate the age of the rocks, now by this time, you had enough technology available by which you could calculate the age of the rocks. So, when he observed the rock samples, for example, in the region of Atlantic, he noticed that in the entirety of the region of Atlantic, and observe this carefully, in the entirety of the region of Atlantic, none of the rocks are more than 200 million years old. Now, this is very unique because in the region of the continents. You will find evidences of rocks which are 2 billion years old, 2.5 billion years old, in certain areas, even 3 billion year old rocks you'll find. But underneath the oceans, he could not find any rock which was older than 200 million years. What did that mean? That meant that the oceans, the crust of it, is being created much later than the continental crust. Now, he also observed that in the region near mid-oceanic ridges, what do we understand by mid-oceanic ridge? What is a ridge, first of all? Many of you would have heard the term ridge for the first time. So, what do we mean when we talk about ridge? So, when we talk about a ridge, here you will observe, Mohanraj, in prelims, you get 15 to 16 questions from geography, and in mains, 110 marks from geography out of 250. So, ridge is a kind of an upraised feature. Upraised feature of sorts. Very good. Kambapati, Rohit, Smita, Kuraku, good. So that is what you find as a kind of a ridge, an upraised portion. And that is continuously present in the oceans across the world. If I can show you the image, observe this image. Now, this is the image showing the mid-oceanic ridges, the ridges under the ocean. Now, this is the region of the Atlantic Ocean, this is the region of the Pacific Ocean, the Indian Ocean, the Southern Ocean, and the Arctic Ocean. I hope we are aware that there are 5 oceans in the world. So, in all these oceans, you will find the presence of these ridges. These, in fact, represent a continuous landform of upraised portions which have an extent of thousands of kilometers, more than 60,000 kilometers long is the extent of all the various different ridges. So Harry has basically observed that near the mid-oceanic ridges, the rock samples were younger. They had been created very recently. And near the oceanic trenches, what is a trench? Trench is a narrow, deep depression. When you think about a trench, trench is like a narrow, deep depression, right? For example, Mariana Trench in the region of Pacific has a depth of close to around 11 kilometers from the sea surface. Peru-Chile Trench to the west of South America has a depth of around 8,000 meters from the sea surface. So these are your trenches. So Harry has basically observed, if I draw this continuously, let's suppose I draw this as a continuity. So this is your ridge, this is your trench. So he observed that near the mid-oceanic ridges, near this portion, rock samples have been younger. They are very young. There you will find newer rocks. Here you will find very old rocks. Old rocks, right? So rocks are oldest but less than 200 million years. On the crest of these ridges, crest means top. On the crest of these mid-oceanic ridges, cracks with the continuous active volcanic eruptions were found. So these were the regions where you had so many cracks that you had active volcanic material coming out. Active volcanism was observed here. Now, age of rocks and types of rocks may be similar for any two places equidistant from either side of the crest of the mid-oceanic ridge. That means if I consider a rock somewhere here, and if I consider a rock somewhere here, in the sense that they are equidistant from the top of the mid-oceanic ridge, now they will have the same age. These both will have the same age. Right. So these were few of the observations that Harry Hess had made. So based upon these observations, he propounded what was referred to as the seafloor spreading theory. Now, if I talk about it again, about the all these observations I will summarize again. But what was his theory? His theory was that newer crust gets created underneath the oceans, and the older crust that gets destroyed at the region of the oceanic trench. That is where it is consumed in the region of the mantle. And because the surface area of the planet remains the same, it is not as if the size of the planet is increasing or decreasing, because if the area of the planet remains the same, and substantially and simultaneously there's a creation of a newer crust continuously happening, means what? It means the existing land masses can be pushed aside by the creation of this newer crust. He said that while the crust in the region of the continents, they remain as it is, the crust of the oceans, that continues to get circulated and that continues to get regenerated. So that is why you observe newer rock samples in the region of the oceans. And just to substantiate that, observe this image. This is an image from NOAA, that is basically National Oceanic and Atmospheric Center in US, which is responsible for carrying out the scientific studies of atmosphere and oceans. So this is as accurate a map as it could be. Let me first of all explain to you what this map represents. The coloration that you see, not on the continents, but in the oceanic areas, right? So the coloration that you see, that provides you with the age in terms of millions of years. So wherever you find the reddish color, that means that particular region has an age less than 20 million years. So that is very, very new. Whenever or wherever accordingly you see the coloration as green in majority of the areas, they have been created 120, 130 million years back. And then the purple or the pink coloration, that means there the crust is older than 250 million years. So now observe all the oceans, right? This is a map which is quite significantly helpful to help you understand about the crustal age of the ocean. So observe, here you have a newer crust, here you have a newer crust. As you go away from the mid-oceanic ridge, the crust gets older on both sides. Eventually, it is the oldest. Where? Here. It is the oldest. Where? Here. So that means near the region of near the area of the mid-oceanic ridge, here in all these places, due to active volcanism means what? Where there is a continuous volcanic activity. So because of that active volcanism, in all these places, you observe the creation of a newer crust, whereas the older crust gets subsumed somewhere. One thing, if you can notice and observe here, observe the presence of pink coloration here, right? In the region of the Mediterranean and the Aegean Sea. The Aegean and the Ionian Sea are present here. Today I will give you those areas to point it out on the map also. Now observe how old it is. That is one of the oldest oceanic crust that you will come across. That is somewhere close to around 250 to 280 million years old. That is why in the modern time and age, many of the scientists, they propound that this is the remnant of the old ancient Tethys Sea. Tethys Sea, which was present as India moved ahead and collided with the Eurasian landmass, leading to the formation of the Himalayas. So the Tethys Sea, which was present, this is a remnant of it. At one point of time, this ocean would be continuous across this entirety of the area. You would only have water body, and Indian landmass would have moved from here. But nonetheless, coming back to it again, coming back to the seafloor spreading. Seafloor spreading means what? The entirety of seafloor is spreading in terms of its area. How can the seafloor spread? How can the seafloor become wider? So while I cannot provide you animations here, think about it. At one point of time, North America was very much joined with the region of Europe. South America was very much joined with Africa. But then, in the last 200 to 225 million years, you have, or the planet has witnessed, the expansion of the seafloor in this region and creation of that vast Atlantic Ocean. So, that is the seafloor which is spreading. So, how is the seafloor spreading? Seafloor is spreading because of active volcanism in the region of these ridges and the older landmass being consumed at the region of the trenches. So, if you can think about it, the creation of a newer crust, basically, let's suppose this is your existing crust in the region of a mid oceanic ridge. Let's suppose there's an existing crust. Okay. Now, heat is provided from the interior by some process or the other. Let's suppose heat is provided here. Now, I hope you would have at least, regardless of whichever part of the country you are coming from, north, south, east, or west, I hope you would have seen, if you have not cooked yourself, someone else cook the chapatis. I hope you would have seen that, isn't it? That someone, how do they cook the chapatis on fire? Now, when you put the chapati on a fire or any kind of a bread or any kind of thing on fire, what happens immediately? Immediately, you will observe it after it gets heated up, it starts to swell, isn't it? It starts to swell. But beyond a point, it cannot swell. If you continue to provide heat after that also, what happens? That swollen portion, it starts to burn a bit, it starts to break and crumble. And the entire swollen portion of the chapati then deflates, right? I understand it is getting deeper into the cooking aspect, but I hope you are able to relate to it. Why I want you to relate to these examples is because these events have happened over such a long period of time. Unlike the perspectives that you get in other subjects, such as let's suppose any other area where you have the videos available about what has happened, here nobody has witnessed this. We have basically come to this formulation based upon the present experiences, present observations, and a calculation of what would have happened in the past. That is why always advisable to link geography with the basic concepts or the basic events that you encounter on a day-to-day basis. So as you heat that chapati, it inflates, it basically fills up with air, and then eventually it cracks open. Similarly, as the heat is provided, here also, the land will get slightly inflated because we are talking about the crust. In comparison to mantle, core, etc., crust is made up of the lightest materials, the least dense materials. So the land there also tends to inflate after getting heated up. Then it cracks open, right? And after that, as it cracks open, here you have volcanicity. Volcanic materials start coming out. Now, few of us, we have never heard about underwater volcanism. So for us, it might be difficult that how come volcanic events happen underwater. But just to tell you, majority of the volcanic events across the world that you observe, that happen underwater. That is underneath those thick water column of 3 to 4 kilometers. That is where the volcanic eruptions, they keep on happening. Now, these volcanic eruptions, which keep on happening from time to time, they basically break the crust and newer materials come out. So, as the newer materials they will come out, they will solidify, pushing the older materials to the side. So, what you observe as a phenomena basically is the older material of the crust. Let's suppose that is pushed aside. Okay. And in the meanwhile, The newer materials, they get created here. Okay. Now, again, after some time, more heat will be provided, because the production or the provision of heat is a continuous process in certain areas. The production of heat, because when I tell you that heat has been provided temporarily in that region, now temporarily for geography is very different as you compare it to, let's suppose, a subject like history or polity. Because in geography, when we say recently, we mean 2 to 3 million years back. In geography, when we say near future, we are talking about 100 million years down the line, right? So temporarily means for a few million years continuously there is heat which is provided, right? So here, when you have that further heat being provided, what will happen? The newer crust will again inflate, get broken up, isn't it? So that will lead to a situation where you have the older crust and then the earlier created newer crust, and then maybe another crust which has been created. So like this, it is a continuous process. Now, that is why he said that newer crust gets created at the mid-oceanic ridges. Now, imagine if there would have been a landmass here. Imagine if there would have been a landmass here. Now, as this newer crust is getting created time and time again, what will happen to this landmass? This will get pushed away from each other. That will be moving in a direction away from each other always. Isn't it the case? So that is where the existing land masses, they would be moving aside. Whereas the destruction of the older crust does happen in the region of the oceanic trenches. That is what he said. Now, in the oceanic trenches, you will have a situation. If suppose this is the oceanic crust, here let's suppose you have a continent or another oceanic crust. Here you have water. So this is your oceanic trench. So as the existing crust gets pushed aside, eventually it will get pushed down, right? And that is where the older crust is being consumed. That is what he said. Now, this is the entire encapsulation of his seafloor spreading theory, which could then explain why the oceanic crust is so younger. Because Harry has said that unlike the continental crust, oceanic crust keeps on getting recirculated. Recirculated means it is fresh in circulation. Where newer crust gets created, the older crust is destroyed. Again, a newer crust gets created, again, the older crust is destroyed. So this process continues eventually, and that is how you have the entire mid-oceanic ridge or the expansion of the sea floor, and that expansion of sea floor is leading to movements on the planet. This was his theory. Obviously, this theory also had limitations. For example, does the older crust get destroyed at every oceanic trench? What is the mechanism of destruction of the older crust? Okay, your theory explains about the mid-oceanic ridges, but what are the other different features present underneath the water? Who will explain that? So his theory had various limitations and drawbacks also, because of which certain aspects of seafloor theory, seafloor spreading theory, was eventually rejected. Some parts were accepted. But eventually, this led us to formulate the plate tectonic theory in a much more concrete manner. So his theory basically said, the theory in itself, that active volcanism leads to creation of. I will tell you everything about the formation of trenches also, about underwater volcanism also. I will tell you everything. Immediately after this, we get into plate tectonics. That is the theory which is acceptable. I will tell you all details about it. Why oceanic crust, heavier, lighter, everything we will cover. But here, I want you to get yourself familiarized with the other concepts which help the scientists formulate the plate tectonic theory. That is why we are going through this process. Okay, so don't worry. Trenches, etc., you will be taught about it. Active volcanism leads to creation of a newer crust at mid-oceanic ridges as the older crust is pushed aside. The older crust of the ocean is consumed at the oceanic trenches, which leads to circulation of oceanic crust. And this is the reason why, as per his theory, this is the reason why, as you would move equidistant away from the mid-oceanic ridge, let's suppose you are talking about a rock here and a rock here, they are of the same age, right? As you talk about, let's suppose a rock here and here, they are of the same age, because they would have been created at the same time. But then the creation of a newer crust would have pushed them aside. Now, if I can take you back to this image once more, observe this. This is your mid-oceanic ridge. This is your mid-oceanic ridge. Okay. Now here, you would observe that this is where the newer crust is getting created. The older crust, this is 60 million years or 80 million years old. Then further older crust, 120, 130 million years old. Then 180 million years old, 200 million years old. So the older crust continuously gets pushed aside as the newer crust keeps on getting generated at the region of the mid-oceanic ridge because of active volcanism at the mid-oceanic ridge. Harry Hess did not say why there is active volcanism at the mid-oceanic ridge. It is later on the scientist basically he said that he would have meant that these volcanism would have happened because of convection current, etc. But Harry Hess in his theory, he never clarified that why you will have fresh volcanism at the region of mid-oceanic ridges. He only talked about the volcanic activities at mid-oceanic ridges, that there are so many volcanic eruptions that their materials, they will come up, they will solidify, pushing the older materials to the side. More materials will come up, they will solidify, pushing the older materials to the side. This process continues, and eventually the older crust will get side or will be pushed to the side and newer crust gets generated. A similar event, he said, is not present in the region of the continents, and that is why the continents, their rocks are so very old, whereas in the oceans the rocks are so very younger. That is the entire aspect of seafloor spreading. I hope that is understood. Now, don't weigh this theory on the current principles, that whether this is still happening or not happening. We'll come to the principle of plate tectonic, which drives our understanding of what happens today. But that derives substantial amount of evidence from all the supporting theories which have been given earlier. Okay, so this is your seafloor spreading in a gist, where Harry has said that newer crust gets created in the oceans, the older crust gets consumed at the region of these oceanic trenches. Having said that, his theory also suffered from severe limitations or drawbacks. Amongst the limitations or drawbacks, It does not explain the small features of the continental floors. Presence of plains, seamounts. Seamounts, what are seamounts? Now, the name in itself tells you seamount. It is an underwater mountain. So, I hope we are aware that even in the oceans, the vast oceans that we come across, uh, inside them, you have very tall mountain peaks, very tall mountain peaks. Because the depth of the ocean in many of the regions is around 6 kilometers from the water surface, 5 kilometers from the water surface. Now, from that region itself, the mountains rise up, and few of them they manage to rise up even above water. So, you have very tall mountains underwater. Had they been present on land, they would have been covered in snow and ice. That is how high they would be. So he did not explain that how these seamounts were created. It was during one of these expeditions in the Pacific that Harry has basically observed that you have a very unique feature underwater, where the underwater mountains, if this is the water surface, underwater mountains, they have been eroded in such a way, they have been degraded in such a way that they present a kind of a structure like this. He named this feature after his fellow professor in the university, and he named this as Guyats. We will talk about all these when we come to oceanography, that how they get created, what is their properties, etc. We will study it, all of them in detail. This is just a kind of a familiarization of the name. So he did not explain the formation of any of these. Then it does not talk about the movement of the continents, about the volcanicity in continents, because volcanic eruptions happen under the continents also, right? You can have creation of newer crust under the continents also. Seafloor spreading theory is silent about that. It does not speak in terms of lithospheric regions, that which, when we say the creation of newer crust, only the newer crust will get created or a new lithosphere will get created. Because lithosphere is what? Lithosphere is crust plus solid upper mantle. So he talked all the meanwhile creation of a newer crust, consumption of the older crust. He only talked about in the terminology of crust. So the entire lithospheric region he did not specify about. That is another drawback. One of the other drawbacks is, as per his theory, wherever you have the creation of a newer crust, the older crust will get consumed in an oceanic trench. But not every ocean on the sites will they have an oceanic trench. Oceanic trenches are limited in certain areas. So that entire circulation is not as smooth as Harry has had propounded. But nonetheless, the contribution of seafloor spreading theory was quite significant. It helped us understand the plate tectonic theory. So Harry Hess and his seafloor spreading, basically American geologist, naval expeditioner, corroborated the fact that the continents can move, and it formed the basis of the plate tectonic theory. It was the first comprehensive theory to talk about the movement and formation of the seafloors. Simultaneously, other scholars such as Mackenzie, Parker, Wilson, Morgan, all of them in the 1960s developed a more comprehensive understanding of the movement of different parts of the Earth crust, both oceanic and continental, and its related formation. It is explained under the theory of plate tectonics. Now, we come over to the plate tectonic theory. Basically, whatever Harry Hess had said, that yes, there is a creation of a newer crust, the older crust gets consumed, whatever Alfred Wagner had said, that the continents can drift, whatever Arthur Holmes had said, that you have generation of a convection current in the mantle, all these different aspects, they led us to formulate the plate tectonic theory. Now, plate tectonic theory is not always credited to one individual, because you had many of these scholars working in Princeton, working in Cambridge. All of them basically they started submitting their own formulations or postulations about, and their own theories about what is determining the movement of the land masses on the surface. And a compilation of all their studies led us to formulate the plate tectonic theory. Now, plate tectonic, this is a very weird name, I'm sure. In your common English language or your lingo, you would never have come across this term tectonics before. So, what is this tectonics? It is derived from the term tectonique, which means building, right? The act of building. So, plate tectonics. So, it talked about the entire lithospheric region, the entirety of lithosphere. Lithosphere, I will again specify, just so that you don't get confused that earlier you had said that the top of mantle is molten asthenosphere. That is not the case. Lithosphere represents upper crust, or rather the crust, plus solid portion of upper mantle. Okay, so that is what is represented by lithosphere. Now, the plate tectonic theory said that the entire lithosphere is actually broken up into various different plates, various different subcontinents, subparts, and various different plates. Now, all these plates, they continue to move over the region of asthenosphere, and they move over the portion of asthenosphere with respect to each other. And in that process, they basically end up creating the land masses. That is it. That is what the plate tectonic theory said. Now, here also, if you observe it carefully, the theory does not tell you that why the continents will move. Later on, people devise that mechanism why these plates will move, etc. But the theory simply tells you that the lithosphere is broken into subparts, that is plates, and these plates they move with respect to each other. That's it. Now think about it. Almost 50 years back, Alfred Wagner had suggested the same thing. His reason was wrong. The mechanism that he demonstrated was wrong. Here, they did not present the mechanism itself. Because Wagner's mechanism was wrong, he was ridiculed, he was made fun of, his theory was rejected. But here, the theory was accepted. Right? That is the hypocrisy that you will observe. Because here, obviously, this was done on the US soil, on the face of the US universities and the US scholars. So this was readily accepted. But nonetheless, over a period of years, this plate tectonic theory has furthered our understanding about the Earth's interior and how the Earth's interior they function, they move, etc. So they said that lithosphere is broken into different plates. Now, these plates they move over the region of asthenosphere. The movement is driven by the internal heat of the Earth. Wherever there is provision of heat, there can be a movement associated. Now, based upon the size, these lithospheric plates, they were divided into major and minor plates. Major plates and minor plates. Right? Major and minor plates. So the lithospheric region gets divided into major and minor plates. Now here, if you will observe, the plate distribution or the classification of the, or rather the plate boundaries overall, this is the world map indicating the various different plate boundaries. If you observe, for example, the Eurasian plate, for example, the Indian plate, which is the Indo-Australian plate, the African plate, the South American plate, North American plate, Pacific plate, part of Australian plate, Antarctic plate. Now, these are your large plates, major plates. So, almost all the major plate you will find will have the presence of both continental as well as oceanic crust, almost all of them. Right? So, all the major plates you will find the presence of continental crust also, oceanic crust also, continental crust also, oceanic crust also. Continental crust also, oceanic crust also. So all these plates will have the presence of both of them. Amongst the major plates, the Pacific plate is the only one which is consisting of only the oceanic crust. Pacific plate does not have a continental crust in it. It has only presence of oceanic crust. Okay. Now all these plates are in motion with respect to each other, right? And that is how you have the movement of the continents or the oceanic region. Their size increases or decreases over a period of time. Now here, if you think about it, why will the plates move in the first place? Why do the plates move in the first place? So let us understand that. Here, if you consider this, again, the same experiment for the convection current. You can carry this at your home also, and you will find the same result. Many of you would have observed this beforehand also. So let's suppose again, you consider a larger utensil. Now this time you keep a lot of water on that. Okay. Right. Now let's suppose you keep on top of this two cubes. Let's suppose you keep two wooden cubes here. Something which is floating on the water, a thermocol cube, anything. And then you provide it heat. Now, initially, these cubes A, B, they are very close to each other. They are next to each other. Now, as you provide heat, after some time, what do you observe? You will have the presence of a convection current here. You will have a presence of a convection current here. Now, after some time, you will find that A and B, they move away from each other, isn't it? So A and B, they keep on moving away from each other. So this is a movement which is observed in the case of the plates also, where the argument is very simple, that in the region of the mantle, convection current in the region of mantle makes the plates move with respect to each other. Okay, so think about it. Let's suppose when you consider the portion of the plates, the lithosphere, and then the rest of the mantle. Let's suppose this is your lithosphere. This is the portion of your rest of the mantle. Here you will have, let's suppose, the asthenosphere. Here you have the rest of the mantle. So you have convection currents which are generated. Now convection currents can either be like this from the entire portion of the mantle, or in certain areas the convection currents can also be very small, restricted in asthenosphere itself. Nonetheless, regardless of the convection current or the thickness or the width of the convection current generated, it will lead to the same instance or the same result. That is, the vertical component of the convection current will heat up that lithospheric region. So that lithospheric region will swell, then will crack, will break. And meanwhile, the horizontal component of this, just like here, the horizontal component of the convection current would pull the blocks apart. Here also, they could pull the land apart. So that is how. And after that, the vertical component will lead to the creation of a newer crust in many areas. So that is how these convection currents, which are present in the interior, they end up creating the movement of the plates. Something that Harry Hess had already said when he was talking about the seafloor spreading theory. But then he observed that underneath the oceans of the world, the creation of the mid-oceanic ridges, creation of newer crust, that is where he observed this. So that is where you have the convection cell in the region of the mantle, and that heats up the region significantly. And you have active volcanism here, and the older one plate gets moved aside. Now, what if you have the convection current underneath the continent? Underneath the ocean, we have seen. Fair enough. The oceanic crust is around 5 to 10 kilometers thick. So fair enough, it is easy to puncture the oceanic crust. So it is understandable that why you have active volcanism. But what if you have a convection current underneath the existing continent? For example, as we speak, Africa has been experiencing this convection current in the interior of it for the past many million years. This is the reason why you'll find even in Africa, the region creation of a new Red Sea that you observe. If I take you back to this, so Africa, for a long time, this portion of Africa was very much joined with the portion of the Arabian Peninsula. This portion was joined with this. But in the recent past, you would observe that you have the creation of newer water bodies because the land has drifted apart. Now, as we speak, there's a convection current in action in this area. That is where you have the old volcanoes of Mount Kilimanjaro. You have the large lakes of Lake Victoria, right? So, all these are Lake Tanganyika. That is where the convection current is actually happening. So, if you think about it, what happens if the convection current is present in the region of the continents to the interior? The answer is very simple. Something very similar to what happens when, let's suppose, if you have carried out other experiment in your childhood days. Basically, if you would have held a plastic scale or a plastic ruler in your hand, I'm sure most of you would have had that in your childhood days, right? And then if you keep it above, let's suppose, a candle. Now, is it the case that if you keep it above candle, it starts, the entire plastic melts and starts flowing like a liquid? No, it slightly burns. Then in this region, it will start to grow weaker and weaker and thinner at the same time. And as you pull this away, right, it will get thinner in between. Here it will get thinner and thinner. Eventually, what will happen? It will break away, isn't it? That is something you would have observed earlier. Something very similar happens if you have a convection current under the continents also. Initially, if you observe, you will have that heat, the vertical and the horizontal component will be associated. Now that heat, it starts thinning out the surface. The surface starts to become thinner and thinner as the land is pushed aside. Now observe here, the surface has developed a slight depression. So from the nearby oceans, wherever there is access to oceans, water will come in and fill this up. You will have the creation of a shallow sea or a water body like this, like what we observed in the case of the Red Sea. You will have the formation of a water body. And again, as the convection current continues, observe what was earlier a joint land mass that has been broken into two different land masses. And those land masses are moving away, and you have a new oceanic crust and the formation of an ocean also. If you want to think about the entire process in a much more representative manner, observe this. This is the entire formation. So this is your when the convection current is happening underneath the continents. So this is where you observe that as the continental landmass is being pulled aside, right? Observe that how in between the land simply starts to sink. It starts getting thinner because as you pull the land aside, what will happen to the land in between? It has lost its support base. So it will start falling in. So observe here. It is in these areas where the land is getting pulled away. Right? So that is where it is getting pulled away. And this intervening land, it simply sinks. So the process which unfolds is that initially, when you have that heat which is provided, observe how the land swells, it develops certain cracks also, isn't it? The land swells, develops certain cracks, just like how I told you that if you remember the analogy with the kind of a chapati, cooking of chapati, something very similar happens. Then as the land starts getting pulled away from each other, you have the creation of a structure somewhat like this, where the central portion simply falls. Observe this. This is the region of Africa, the Rift Valley in Africa. These are areas known as Rift Valley. We will study about Rift Valley also in detail in later portion. But when you talk about the name Rift Valley, Rift, Rift is what? Rift is an English terminology. Rift means what? There is a growing rift between India and Pakistan. The rift between the brothers grew larger and larger. Means some kind of a tension, right? Some kind of lack of normalcy. There's a tension. So Rift Valley here represent what is a valley? Valley is a kind of a depression of sorts where the height is or the altitude is lesser than the surrounding. So because of that tension, you have the central portion which sinks. So that is why you have these rift valleys. As this continues, observe here, a shallow sea gets created. Example, Red Sea. A shallow sea gets created. And as this continues further, a larger ocean gets created with the creation of a newer crust continuously happening here. The example is the region of Atlantic Ocean. So overall, this theory combines the benefits presented or points presented by all the other theories that we have talked about. It compiles it quite significantly in the form of the seafloor, or rather the plate tectonic theory. So here, when we talk about the various different plates, now all these plates, they do move based upon that heat provided from the interior. Now there can only be three different types of plate movements. Ones where the plates they move towards each other, another where the plates they move away from each other when the plates they move parallel to each other. Only these three kinds of plate movements can be observed. So here, when we say the plates and their movement, so think about it. If let's suppose you have two plates, they can move away from each other, they can move towards each other. So how will they move towards each other? Let's assume here you have presence of three different plates or four different ones. Now, if there's a convection current here, if there's a convection current here, so that means these two will move away from each other. These two will move away from each other, right? If I name A, B, C, and D, A and B are moving away from each other. C and D are moving away from each other. But B and C, they are moving towards each other. So that is a kind of a convergent or towards each other. They are known as convergent plates, converging plates. When they move away from each other, they are known as divergent plates or diverging plates. And when they move parallel to each other, When do they move parallel to each other? So if, let's suppose, if you take a look at it from a top view here, if this is plate A, this is plate B, as you take a top view, if they are moving like this, right, it is a transform plate. So that is parallel to each other. So we will consider each one of these cases. We'll try to understand how is it that the plates move, and once the plates do move, what are the different types of landforms or observations that are created as a process. Okay. Why in the case of Rift Valley, volcanic activities are not seen? It is observed in many of the rift. For example, in African Rift Valley, you do observe volcanic eruptions. How does the water come when the sea gets created from a rift? From a nearby ocean. So, for example, if I can take you back a few slides. So, this is, if I can take you back here. Now, as I told you, Africa is breaking. Now, suppose there's a rift valley which is created from in this area. There's a depression. So as the entire rift valley will further deepen, what will happen? Water from here will get inside. Water from here will get inside, isn't it? So here, after some time, you will have a creation of a narrow sea in this region. As the convection current continues to happen, this will further be pushed away from each other. Mid-oceanic ridge, new volcanism will be observed here. So eventually, after many millions of years, you might have an ocean to be found in this area, right? So that is how you have the water filling up these depressions overall. Okay. What is a plate? Plate is basically the lithospheric region broken into small subparts. That is a plate. How much time does it take during the process plate move? Plates basically they end up moving at different speeds. Many of the times they can move at a speed of 1 to 2 centimeter per year. Sometimes in certain areas they can move at 10 centimeter per year. But at max, that is the speed, presently at least. You don't have a plate movement faster than that. The older crust, we'll talk about it. What happens to the older crust? Vishwas, the speed of seafloor spreading across the globe are same? No, absolutely not. Is it the Tethys Sea that caused the Arabian Peninsula to have large number of oil reservoirs? Yes. And parallel plates. Parallel plates, basically, if you do these plates experience force of buoyancy? No. Isn't the plates crust? No. Plates are basically the crust plus the upper portion of mantle also. That is the portion of the plates. Now, parallel movement of plates, if you consider them, here, let's suppose you have a large plate here. Every year plates move, continuously they move. If the plates moving parallel to each other, then there is convergence at one side, divergence at another side. So we are talking about 3 dimensions of 3 sides. Yes, we are still in 2 dimension because you have the plates, they can move away from each other, they can move towards each other, or they can move parallel to each other. So we are still talking about in 2 dimensions. So here, when we talk about it, let's suppose you take a top view. This is your top view of two plates. Top view. Now here, if this is a plate A, this is a plate B. Now, suppose both of them are moving away. Due to convection current which is present in the interior, the plates are moving away. Now, these plates can be thousands of kilometers long, tens of thousands of kilometers long. For example, even if I show you the region of the Atlantic Ocean is also moving away from each other. Here also, the plates are moving away from each other. Here also, here also, here also, and here also. But if I ask you a question, Can it be possible that the rate of movement here in the region of Iceland is similar to the rate of movement here in the region around Antarctica? Can that be possible? No, it cannot be possible. You have so many variables in place that it simply cannot be made possible. So, it might actually happen that the rate of movement in this portion, let's name this portion as 1, the rate of movement in the portion around 1 is very different from the rate of movement in the portion around 2. Maybe here, the movement is happening at maybe 5 centimeter per year. And here the movement is only happening at 1 centimeter per year. What will happen? There will be tension which will be developed. There will be a crack which will be developed. Let's suppose a crack has developed on this plate here. Now, this is B1 and B2. Now think about it, B or B dash. Think about it, B and B dash, they are both moving in the same direction, but they are moving at different speeds. One is moving at 5 centimeter per year, another is moving at 1 centimeter per year. It is a movement in the same direction which is happening, but happening at different speeds altogether, right? So that is where you have the parallel movement. Why the rate of movement is not always the same? Because the rate of movement is dependent on many factors. The amount of heat which is present in the interior, the thickness of the crust in certain areas, the presence of other undermining factors, that where the heat is getting released in many of the portions, the width or the dimension of the plate involved. That is why the rate of movement is going to be very different. Okay. Is there any evidence that previous ocean is converted to landmass recently? See, margins of oceans, they get depositions of sediments. You have the creation of certain land masses there, but it is not the case that a large ocean will suddenly become a land area and a large land area suddenly becomes an ocean. That is not the case. Okay. If the country A plate joins with country B, then to what particular plate it belongs to? Plates are not dependent on the country boundaries or either the continent boundaries. Plate boundaries are much beyond that. That is why, if you observe this image here carefully, observe this. It is not by any particular boundary. Here, when we consider the North American plate, it also consists of the portion of Atlantic Ocean. When we consider the Eurasian plate, it consists of the region of Asia, Europe, Atlantic, Arctic Ocean as well. When you consider the African plate, parts of Indian Ocean, Southern Ocean, Atlantic Ocean, the part of Mediterranean Sea, all of that is considered. So it is not uh, restricted by the limitations of boundaries, so to say. Now we come to each of the plate movements and let us try to understand that what kind of events unfold. But before that, we take a break. And after that, we continue further. In Japan, new land was created recently. It is not the case, my dear friend. All of you are so very entangled or so very distracted by that news that in Japan, new land has been created. Such lands, they do get created. It is just that you are observing it now because you are observing the portion of current affairs maybe now recently. But previously also, in the past decade or so, Pacific Ocean in itself has observed the creation of many such islands, many such landmasses. But can we say that Pacific Ocean has converted into a landmass? No. If this was the ocean, at max, now here you will have a kind of a landmass which is protruding above it. That's it. Right? But nothing more to it. Okay. Unni, my dear friend, listen to this very carefully when I reply to you for the second time now. Why do they move at different rate? Why do the plates move at different rate? Listen to this carefully now. When we talk about the heat getting supplied in different regions of the planet, it is not a uniform form of heat. Heat has got its variation in different areas. It might be possible that the residual heat being provided in certain region is furthermore supplemented by the radioactive heat provided from the interior. The dimension of the plate is also going to be different. So that is why the movement of the plates is always going to be different from one region to another. As we talk about the Indian plate itself, its movement at one point of time was 20 centimeter per year. Now the movement of the Indian plate is happening at the rate of 1 to 2 centimeter per year. So it depends significantly on the strength of the convection current, the position where the convection current is happening, the location of it, where it is happening, whether it is offset by volcanic eruptions, etc. So that is why different plates will always indicate different rate of motion. Okay, right. So now let's take a break and we come back after the break and we continue. So 10 minutes break will do, I think. Okay. So we take a break for 10 minutes and then we continue. Okay. 15 minutes. Okay. Be back by 8:05. We continue after that. A confirmation about the audio, please. If the audio is clear and available, kindly confirm. Thank you. Do we study the Pacific Ring of Fire here? Yes, you will study that also. Don't worry. Okay. So now, let us try to understand what actually happens when these plates move. So, when we talk about the plate tectonic theory in the entirety, so let me simplify it for you guys also, because it can lead to certain confusions here and there. So, if I have to simplify the theory of plate tectonics, let's suppose, generally for anything, when you are studying it for civil services, the aspect of it that you have to address is W3H, isn't it? When, where, why, and how. So, here, what is it? First of all, what are plates? That is the first question that you need to address. So, I hope we all know that. What are plates? Lithosphere is broken into small parts. Lithosphere is broken into subparts. Okay. Why do they move? Due to heat from the interior. Heat from interior. How do they move? Towards each other? Towards each other? Away from each other? Or parallel from each other? Right? Now, it is in this process of movement that they end up creating various different types of landforms, associated landforms. So, convergent plate boundaries. That is when the plates are moving towards each other. Now, where is it happening? Amongst the various places, even India is moving into Eurasia. When we talk about the other regions where you experience this kind of a plate movement, if I can take you back to the image of all the plate boundaries, here, observe this image. Here also, observe the western edge of South America. Here, you have a minor plate with the name Nazca plate that is basically colliding with the South American plate. So, here again, convergence is happening. In this portion, North American plate is moving in this direction, and that is overriding in some portions the Pacific plate. So, here also, convergence is happening. Observe here in the region around Japan. Here, in this region also, there is a convergence which is happening. Observe here in the region of eastern portion towards the east of the Great Barrier Reef and the Coral Sea, and around the region of southern Pacific around Tonga Islands. Here also convergence is happening. Here also Indian plate is converging with the Eurasian plate. Here, when we talk about the region of African plate is also converging with the region of the Eurasian landmass. So convergences are happening in various different places in different areas. Now, always remember, whenever two plates will converge, whenever they will collide, the heavier of them, they will start to subduct. And when we say subduct, what you can see in the images, so the heavier of them, they will start to subduct, and the lighter one stays or remains at top. Always. It is the heavier plate which will subduct, and the lighter plate will remain on top. Okay. So heavier plate subducts. Heavier plate undergoes subduction. subduction. Now, after that, when we say that the heavier plate has undergone subduction, now when we say the oceanic and continental plates, which is the heavier one amongst the oceanic and continental? Yes, Shreyas. Amongst the oceanic and continental, which is the heavier one? I don't think there should be any doubt in that. Perfect. Correct. No, Smita, Shovik, you guys are incorrect. Rest majority of you are correct. Seema, incorrect. Always oceanic plate is going to be heavier. Oceanic plate is heavy. Always. Okay. And guys, I would also like to tell you that for the next 1 hour, 1.5 hours, if you pay attention to what is being taught here, trust me, when we cover tomorrow about earthquakes, volcanoes, etc., separately, or whenever you hear about any aspect of geomorphology, not only will you be able to formulate it, understand it very easily, you will be able to formulate that what will happen in the future also. So please pay attention to this portions very carefully. This is one of those catchment areas from where UPSC picks up the questions very frequently. I'll tell you the kind of questions also which is picked up. I'll tell you how to write the answers also. Now, always the oceanic plate is heavier. Why? Because of higher density, as we have seen earlier is the case. Now, what happens when we take a look at the point of or the process of convergence? So here, before that, let's suppose this is one of the plate, oceanic plate, and the continental plate, which is obviously going to be much thicker than the oceanic plate, right? Now, as they will converge, the heavier one, which is the oceanic plate, that will basically start to subduct. So what actually happens here? This will go like this, and the portion of the continent at the margin of it, this will also get deformed quite significantly, and this starts to subduct. Now here, as this subduction process starts, as this starts to go down into the portion of mantle, then what happens? Basically, it is going to go into the mantle up till a depth of around 200 kilometers, 300 kilometers. After that, melting starts to happen. Many portions, they start to melt. Not everything starts to melt, but many portions within that plate, they will start to melt over because the temperature is so very high. And in the meanwhile, as this plate starts to go down, the portion which has gone down, that will exert a pull which will drag the rest of the plate along with it. How and why? So again, remember a kind of a homemade experiment or a kind of a childhood experiment or playthings that you would have done. Most of you would have seen a toy train. You would have played with a toy train or at least seen somewhere. Now, if you keep it on a table, the toy train is very stable, right? It doesn't fall automatically if the toy train is kept on the table. But when you do one thing, when you take the toy train to the edge and you hang the, let's say, the locomotive or the engine part of it, you suspend it from the table. What happens? It starts pulling, the rest of the toy train also falls down immediately, isn't it? Because of that vertical component of the gravity that is influenced. So something very similar happens here also. The portion of the plate which actually goes down, it manages to pull the rest of the plate along with it. And that is what is referred to as the slab pull. So slab pull is the pull or the force which the remaining portion of the plate experiences as this one portion of the plate goes down. Now you have different types of crust. You have the continental crust, oceanic crust, etc. You have different types of crust. So amongst the continental and oceanic crust, when you talk about the types of convergences, There can only be three types of convergences. Convergences can be continental continental, or continental continental, where the continental crust converges with another continental crust. Then it can be continental oceanic, or it can be oceanic oceanic. So there are these three types of convergences which can happen. Let us take a look at what these convergences are, where in the world they are experienced, and what kind of processes they are observed as a result of that. So we start with the oceanic continental convergence. Example of this, what we have seen with the region of South America and Nazca Plate, also North America and Pacific Plate. Example, South American and Nazca Plate. Okay. Now, what actually happened? So you have the portion of the oceanic crust. Let's suppose here you have the continental crust. Let's suppose like this. This is covered under water. This portion is underwater. Now, if there is a convergence happening at both the ends, now this convergence will continue to happen as long as when? As long as there's a convection current on some side which is pushing this towards each other. So as long as that pressure continues, the convection, or rather the convergence, will continue to happen, isn't it? Now here, what do you notice is, basically the oceanic plate is always going to be the heavier plate, always. Now the oceanic plate will undergo subduction, but we are talking about kilometers thick rocks here, guys. We are not talking about two paper planes moving against each other. We are talking about significantly kilometer thick rocks. Now, these kilometer thick rocks, when they are colliding and moving with respect to each other, will that movement be smooth? Obviously not. That movement will be very rough. That movement will be very, very staggered also. And when I say staggered, what do we mean by that? So let's suppose there's a movement. Think about it. Let's suppose you have the palms of your hand. Now, if you try to move them with respect to each other, there's a kind of a resistance that you feel with your fingers, isn't it? There's a kind of a resistance. You apply a greater force, it suddenly moves. So it is a kind of a rough movement. Similarly, as the rocks also try to move against each other, they will offer each other resistance. But the force of the convection current is such, it makes the rocks move despite that force of resistance. So the rocks will move. So here, as the process of subduction happens, observe the changes. First things first, this portion of the oceanic crust will start going down. It will undergo subduction. Now, as I told you, this process of subduction will not be very smooth. It will not at all be smooth. It will be very rough. So the continental crust will try to get, if this is your oceanic crust, this is your thicker continental crust, as it will try to subduct, there will be impact on the continental crust also, on the margin of the continental crust also. So here, basically, you will observe what? If suppose this is your continental crust, here there will be deformation in the continental crust, significant deformation. And to add on to that, if suppose again this is a continental crust and an oceanic crust is subducting here, even this portion of land will experience resistance. There will be resistance in this region. Materials will start to get accumulated. So here, materials they start getting accumulated, and you have formation of a fold mountain in this region immediately. Now, this is what creates depressions. At the boundaries, you observe these narrow depressions. These depressions are what are known as oceanic trenches. Oceanic trenches. Example in this case, the Peru-Chile Trench. Observe it or locate it in the map after the class. You'll find that. Immediately to the west of South America, you'll find Peru-Chile Trench. Along with that, at the edge that you observe, you will observe the formation of a kind of a fold. Right, the land has accumulated because the continental crust is so very thick and so less density, it easily gets crumpled, it easily gets deformed. So here you will find the presence and the formation of fold mountain. Example, Andes. Very good. In the case of North America, you have Rockies. In the case of South America, Andes. In the case of Africa, Atlas. All these mountains are created because of continental oceanic convergence out there. Now, here, at this point or at this zone of subduction, where the oceanic crust is actually undergoing subduction, as we have already said that the movement is not going to be smooth. But why there is this movement? This movement is there because it is continuously backed by the convection current. So here, as the plates they try to move with respect to each other, they will experience resistance. Slowly and steadily more pressure will be built. Still the resistance is there. Eventually that pressure will be overcome and there will be sudden movement. Whenever there will be such sudden movement, huge energy will be released, huge amount of energy. And that energy will vibrate through these plates in such a way it can lead to the vibration or the shaking of the land masses or the region underwater. That is what we experience as earthquakes. That energy which is released, which basically shakes up the ground surface in itself, that is what you experience as earthquakes. So this is a region, seismic or earthquake zone. So northern portion of Africa, western portion of South America, western portion of North America. In all these places where this type of a convergence is happening, you will experience earthquakes. Okay. Now, furthermore, here the portion of the oceanic plate which has gone down. Now, this oceanic plate consists of oceanic water above it with a width or a thickness of 5 to 6 kilometers of oceanic water. Also, a lot of small sediments would also be there at the bottom of the ocean. You will have sediments, etc. also. Now, all these materials, along with some water, they will start percolating. Some amount of water will also go down, isn't it? It cannot be possible that as the rocks are rubbing against each other, only the rocks will go and water won't be allowed. Water will also seep in. Water will also start leaking through. Now, when along with this water, some sediments, etc., they reach at a depth of 150 to 200 kilometers. The temperature has risen so considerably well at that point of time that some portion of this plate will start to melt, some portion of it, but almost all the water and few of the sediments, they will definitely change state. Water will convert into steam, water vapor. Water vapor as a gas has got a lot of power, isn't it? Along with the sediments, it has got a lot of power, and along with the sediments also it will melt. So steam as a gas will try to rise up always. Now, as the gas tries to rise up, it will bring the molten materials along with it. It will keep on melting the other solid substances in the surrounding. So all these molten materials, along with the gases, they start to rise up. They start to rise up here. They will keep on melting the materials that they encounter in between. And because there is so much amount of gas, why gas? Water gets converted into steam under high temperature. So you have gas which has got high pressure. It will keep on pushing upwards, eventually manages to break through the surface. And you have volcanic eruptions. Volcanic eruptions. In the region of South America, you can take the example. Mount Cotopaxi is an example of those kinds of volcanic eruption, isn't it? So that is how you will observe the creation of these particular kind of landforms, or this is what is experienced in these convergences. I will repeat the entire process again. Whenever you have, let's suppose, an oceanic continental convergence, it is the oceanic plate which, being the heavier one, will undergo subduction. Why the heavier one will undergo subduction? Due to gravity. Think about it in this analogy. Let's suppose you have a thin sheet of iron or steel and a thick sheet of thermocol. If you make them collide, will it happen that the iron sheet will start moving over thermocol? No, that will remain at the bottom. It is a thermocol which will ride on top because of lesser weight and lesser density. Similarly, when the oceanic crust, being of higher density, undergoes that convergence, it is that oceanic crust which will undergo subduction also. Whereas the continental crust, it will get deformed at the margins, at the boundary, creating very deep oceanic trenches. And also, accumulation of that continental crust will happen, leading to the presence of fold mountains at the margin of these continents. At the edge of these continents, you will find such kind of fold mountains. Cascade Range or coastal ranges in North America is also an example. Now, at the zone of this convergence, the movement of the plates, whenever it will happen, it oftentimes will release lot of energy in the process. And because why energy? Because this movement is not going to be the smooth one. This movement is going to experience lot of resistance. Eventually, that resistance will be overcome and there will be sudden movement. So whenever that movement will happen, it will immediately lead to release of that energy, which can lead to the shaking of the ground surface, which we experience in the form of massive earthquakes in the region. And also, as the oceanic plate undergoes subduction beyond a particular depth, you will have the water, sediments, etc., that will melt and vaporize immediately. And these molten materials and the gases, they will start rising up because of high energy. They will start melting the materials around them and they will rise up, and if they break through the surface, they create series of volcanic eruptions. That is why when you take a look at the Rockies in North America, it has a combination of fold as well as volcanic eruptions. When you take a look at the Andes in South America, again, a combination of fold mountains as well as volcanic eruptions. Even in Atlas. So that is a common feature or a phenomena of all of that. Mount Hood also, right? Okay, how oceanic plate is more heavier than the continental plate? How many of us are having that doubt till now? Oceanic plate and continental plate? Okay. Kindly take a look at the recordings now. because we have repeated it many number of times. You would have missed the earlier session. That is why it is the oceanic plate has got a greater amount of density. Good, perfect. See, all of you are giving the correct answer in this. So the oceanic plate has got a greater density of around 3 gram per centimeter cube. Continental plate has got a lesser density. So despite the thickness, the oceanic plate is heavier. Again, use the analogy of a steel bar and a thermocol cube. Steel bar, even though it is much smaller in dimension, much smaller in size, will always be heavier than thermocol. Why? Because of higher density. Okay, you can take a look at it when you take a look at the recordings. Okay, heavier crust will subduct always. Yes, Kiran. This fold mountain is found due to sediment in the oceanic crust. I have read, sir. Please tell. My dear friend, it is a different kind of a mountain that you are talking about. When you are talking about the sediments getting folded, see, observe this here, this sediment which gets created. When it is an accretion of that, for example, in the region around Japan, what you observe, that is where you experience that kind of a folding. But in many of the regions, at the margins of the continents, you have the presence of these plain systems, plain regions. So that gets folded to create these fold mountains. Okay. And map of oceanic continental plates. Why the Pacific Ocean contract and Atlantic Ocean expand? As I told you, Sarthak, the plate movement is initiated because of the convergence, or rather the convection current in the interior. That is why you observe this. Okay. And regarding the map about it, uh, this is your map. This is where you observe the oceanic and the continental convergence in this region, in some parts here also. So, Shalu, what you were talking about, the sediments getting folded, that is experienced in these areas. Right. This is also a kind of a convergence, but it is oceanic continental, oceanic convergence. Here you have oceanic continental convergence also in this area. Okay. So that is basically the aspect of the plate movement in this case. Now, then when we talk about a convergence of oceanic and oceanic plate, then what happens? Vishwas, you mean where we find mountains or hills, it is only the result of collision of two plates? Not always. There are different types of mountains and hills. As we come across, you will get a better idea. Every time a subduction takes place, a fold mountain is formed? No, not always. Right? No, please don't read other books. Just restrict yourself to this one. Now, first of all, pay attention that you understand the things in the class. If you leave it out there that I will read it from the book and then we'll understand, trust me, in this subject of geography, we will be covering many different topics which you won't find in relevance, or which you won't find in presence in the relevant textbooks. Right? So please pay attention in the session. Chances are you will gain here something which you won't find in the book, which will give you an advantage over your competitors. So pay attention in this case. So here, we have given the example of volcanic eruptions because of the continental oceanic convergence, Mount Cotopaxi, Mount Shasta, Mount Rainier, Mount Hood in the North American region. All of them have happened because of continental oceanic convergence. Oceanic plate. Now, when they undergo convergence, then what happens? It is a heavier plate which will subduct, right? And if both of them are oceanic, how do we decide which is going to be the heavier plate? So always the older oceanic crust becomes the heavier one. The oldest oceanic crust becomes the heavier one. Why? Because over a period of millions of years, there would have been multiple different oxidation processes, various different chemical reaction deposits, etc., which would have happened at the ocean bottom, which would have made that region heavier. Right? So always remember that older oceanic plates are heavier. in comparison and will undergo subduction. Okay. Now what happens here? Example, you can take the case of the Filipino plate and the Pacific plate, the Caroline Sea plate and the Pacific Ocean. So those are your various different examples of this. So here Pacific plate is amongst the older ones, so it will always undergo subduction. So if I have to talk about it, the fundamental principle involved will be very same. If this is a plate, here also, if let's suppose this is a plate, oceanic plate, they are not very thick. 5 to 10 kilometers is their thickness. Now let's suppose, okay, this is obviously going to be covered under thick column of water because this is happening underwater. All this is happening underwater, isn't it? These events, they keep on unfolding many kilometers under the oceanic and the sea surface. Now, if there is a convergence happening here, something very interesting unfolds in this case. First of all, at the zone of convergence here also, there will be deformity and deformation which will happen in this region also. Deformity and deformation will happen. Right. Now, that means even in this area, we will experience the formation of an oceanic trench, isn't it? Here also we will experience the oceanic trench. Example of such a kind of a trench is the Mariana Trench, the deepest oceanic trench across the world. Mariana Trench. Now, here what happens? Again, at this zone of convergence, just like the previous case, the movement won't be smooth. Here, as they are trying to move with respect to each other, the movement won't be smooth. So, this will also be a zone of active seismicity or earthquake prone zone. Earthquake prone areas, prone zone. Okay. Now, furthermore, one difference that you will observe from the previous image is in the previous image, you observed the formation of a fold here, fold mountain. In this one, you won't observe the formation of a fold mountain. Why? Why is it that in the previous case you had the formation of a fold mountain? In this case, you will not observe it? Apply your logic. Don't worry. What is the worst that will happen? You will be wrong. That's it. Don't worry about it. Apply your logic. What do you think could be the reason? No continental plate. Okay. Lighter. Okay. Water suppresses it. Okay. Crust is not available. Good. No landmass. Thickness of it. Okay. Both are heavy. Good. No accumulated sediments. Good. Very good. No residue accumulation. Only oceanic plates availability because of more continental plate, because of equal density. Okay. Good. More or less, ocean continental plate is less dense. Good. So, more or less, all of you are correct. Understand this. When we talk about a continental plate, as all of you have said, that continental plate is very thick and is less dense also. So there is significant amount of scope for that to get accumulated and get folded over a period of time. But when we talk about oceanic plate is very thin. right? So you don't have enough materials within them to experience that compression and undergo that process of folding. That is why here no fold mountain will be observed at all. Now, just like in the previous scenario, here also water will start seeping in. Water will start seeping in along with the sediments. Now, all these materials, after reaching a depth, immediately they will vaporize and some portions will melt. So here, the molten portions, they start rising up. And here, breaking the crust will be much easier as compared to the previous situation, because here the crust is not very thick and breaking the crust becomes easier. So here you have underwater volcanic eruption, right? Underwater volcanic eruption. Now, here also, interesting things actually unfold. Now, the plate movement or the convergence will continue up till which point? The convergence will continue as long as there is a convection current supporting that plate movement from both sides. As long as that convection current is there, the plate movement will continue, the convergence will continue, the collision will continue. What if this convergence stops? After the underwater, this volcanic eruption, the convergence stops, the movement stops. What will happen? No further volcanic action or no further volcanic eruption will take place. So, you will have a kind of an underwater mountain which is created, whose height won't be increasing any further. Because if the volcanic eruptions would keep on happening, its height would continue to increase. But if no further volcanic eruption is happening, its height won't increase any further. So this is what creates underwater mountains, what are referred to as seamounts. That some ancient volcanic activity which would have happened, not happening beyond that. So you have an underwater mountain created. Now, what if this convergence continues to happen? As this convergence continues to happen, more materials will start moving down, more materials will start melting. As more materials they start to melt, more materials will rise up and it will continue to erupt. Right? Now, when more volcanic eruptions happen, what is observed? This size will keep on increasing. Eventually, it might happen that it will break through the sea surface. It will emerge from the sea surface, right? And when it emerges from the sea surface, then what do you have? Creation of an island. Just like what you guys have observed in the news stories around the creation of a new land in the region of Japan. Trust the press makers to, or the press guys or the media guys to come up with a catchy news story or a slogan which immediately encapsulates all of you. So that news that you read about creation of new land near Japan, it is not a creation of a new land altogether. It is simply emergence of an island, right? So this creates what is known as an island. Okay, this is what is an island. Now think about it. These plates, their convergence, it is not as if the convergence is happening at a thickness of 2 centimeter or 4 centimeter. The plates can extend for thousands of kilometers. So the scale of convergence, the zone of convergence can also spread for thousands of kilometers. So when you have convergence happening across thousands of kilometers, you will have many such islands getting created, many such different small islands getting created. Many of them will be volcanic in nature, etc. But many of them will get created. This is the reason why the region of Indonesia, Philippines, the entire region, you'll find thousands of small and big islands, archipelago, Indonesian archipelago. Thousands of islands will be there. All of them created due to volcanic eruption. When you observe the region around Andaman Nicobar Islands, Now, Andaman Nicobar, many of those islands have been created by this process itself. This is the reason why the only active volcano in India is found where? Barren Islands near Andaman region, isn't it? Happens because of this process taking place. Right? So that is the process of oceanic convergence. Right? So here, when we talk about it, example you can take of Indonesian islands, right? So these kind of islands will get created, multiple of them. Okay. Tonga Islands is again another example of that. Good, Manish. So you have Tonga Islands, Aleutian Islands, yes. Good, Satyam. Hawaiian Islands don't happen or not created because of convergence. Hawaiian Islands, Reunion Islands, they are not created due to convergence. They are created due to a different property of volcanism, mantle, plume, and hotspot. We will study about it in the next module. So these get created due to the volcanic processes. Any point of time when this convergence will stop, volcanic eruption will stop, and whatever will be the size of the landmass, that will be left behind. Okay. Now, Andaman Nicobar is also an example of this. Mount Etna. Okay. Yes. Andaman Nicobar Islands are also island created by mountain. My dear friend, this is okay. Okay, many of you, when you think about a mountain or an island, rather, when you think about an island, what is the perception created in your mind? That is it a kind of a landmass which is present? Just as, see, understand, islands, it is not as if the islands that you see like this is an island. How did this come into formation? Have you ever thought about it? That how did the island come into existence? Why is it that a region is surrounded by sea? Is it because the god will so, and the god desires it like this, that is why it is like that? No. At one point of time in history, this would have been an underwater mountain. At some or the other point of time in history, this would have been an underwater mountain. There would have been water and it would have risen up like this. Over a period of time, due to multiple different processes of erosion, etc., happening, this region would have flattened out. This region would have flattened out. And you would have had the formation of a kind of an island of sorts. Right? So, everywhere, whenever you see an island, whenever you come across an island, everywhere it is created because of this process of volcanicity. Is that understood? I don't know where the question came from, Rajneesh. Rajneesh and Velu, you also had a similar question. Is that understood for both of you? Good. Right. So that is basically the creation or the existence of the oceanic and oceanic plate. Now we come to the third type of convergence. There's a possibility of volcanic eruption? Absolutely, yes. There will be a possibility of volcanic eruption in this case. Now we come to the third type of convergence. What do you observe in the case of continental plate? Here, the example that you can take is of Indian plate and the Eurasian plate. Example, Indian plate and Eurasian plate. Now, in this case also, both of them are having the same density. Both of them are very, very light. So, which will undergo subduction? So, here also, depending upon the different processes of volcanic eruption, sedimentation, etc., the heavier plate undergoes subduction. It varies which is the heavier one, etc. Out of these two, it is the Indian plate which is heavier and undergoes slight subduction. So, overall, what you observe here is, let's suppose you have a continental plate here. Right? Another kind of continental plate is present here. Both of them are undergoing convergence. Right? Now, when both of them are undergoing convergence, then what happens? So, if suppose this is your portion of Indian plate, this is the portion of Eurasian plate, Indian plate being the heavier and the denser one, some part of it undergoes subduction. But we have light objects which are colliding. So, rather than subduction, what will dominate here is compression and significant folding. So, basically, compression and deformation will dominate over the process of subduction. So, here, as both are light and have less density, compression and deformation predominate subduction. Okay. So here, there will be very little amount of subduction, but compression and deformation of the landmass will be dominant. So what you observe here is basically the land gets deformed into the kind of folds. Multiple folds will get created. The crust will get compressed and will thicken very significantly. Right? Some portion will undergo subduction. Here you have the fold mountain, example, Himalayas, Alps, Appalachian good, etc. Now, as long as the convergence will keep on happening, the height of this will keep on increasing. And here you will observe that the crust has got thickened and has got compressed so significantly, this will become very hard. Metamorphic rocks will get created. Crustal compression and thickening. Some part of the heavier continental crust, it will make its way down, it will continue to subduct. But here you will not experience a volcanic eruption. Unlike the previous two cases, here you won't experience volcanic eruptions. And there are two reasons for that. The first reason is that unlike the previous cases, here you don't observe the percolation or the penetration of water, which will vaporize immediately to provide that steam, which can bring the pressure and bring the molten materials with pressure closer to the surface. So you won't find that, right? And secondly, the second reason will be that the crust will get so very thick, despite the fact that, let's suppose, there are certain molten materials present, they will never be able to make it to the surface. Unlike the case of the earlier two, the crust was not thickened so much. Here the crust has thickened. As you remember, last week we studied that in regions such as the under the region of Himalayas, the continental crust can be as thick as 70 kilometers deep. So that is where the crustal thickening and the compression of it, it is completely constituted of hard rocks. Hard rocks will dominate, and these hard rocks, they will undergo deformation, etc. Okay, so this is the reason why In the case of continental convergence, no volcanic eruptions are ever to be observed. Retain that in your mind, in your memory. If required, write it down somewhere. Why no volcanic eruptions in the case of Himalayas? Right? Why no volcanic eruption in the case of Alps? So, in these cases, wherever continent convergence is involved, no volcanic eruption will be observed because you don't have enough molten materials and gases created and formed in the first place. And secondly, even at the zone of subduction, if there is some amount of molten material created, then even in that case, the crustal thickening and deformation is such that the molten materials won't be able to break through those hardened rocks and those thicker crustal portion. That is why the region lacks volcanoes. Okay, you have to keep that in mind. So overall, these are the different types of convergences happening. Now, in all different types of convergences, you will observe that some or the other portion of the plate is consumed. It is destroyed by subduction or the other thing. Some or the other portion of the plate is consumed or destroyed. So that is why this is also what is referred to as destructive plate margins. Destructive plate margins. Okay, because in all different types of convergences, some or the other portion of the plate is basically consumed. Hence, the convergent plate boundaries, they are also referred to as destructive plate margins. Margin means the boundaries or the bordering areas, hence margins. Okay, so again, this is the different types of convergences. Why not heavier continental plate will go subduct? Who told you that the lighter continental plate will undergo subduction? It is always the heavier plate which will undergo subduction. In the case of the Eurasian and the Indian plate is the heavier one. Okay, Indian plate, the density is heavier. When you think about the weight of it, don't think that Eurasian plate is so very large. So Eurasian plate obviously will be more bulky. Indian plate is small one, it will be lighter one. No, it is not as if someone is trying to put it up on the scale and weigh it down and then, okay, you are heavier, so you will have to undergo subduction. At the zone of subduction, if you consider per unit area, the density of Indian plate is much heavier. That is why, and because of the recent volcanic activities which have happened in the past 100 million years or so, 120 million years or so, that has further added to the weight of the Indian plate. That is why it undergoes subduction. Okay. Tibetan plateau has volcanic rocks. Yes, it does, because of the events which have created them. Even the region of Himalayas, in certain areas, you will find the presence of igneous rocks. Even in the Eurasian subcontinent, you will find the region of uh, igneous rocks to be present. Wait for some time, have patience. This is all due to thermonuclear reactions, not always due to only thermonuclear reactions. The residual heat present in the interior of the earth, that will also generate it. Okay. Dhyan, is there any relation between oceanic convergence and seafloor spreading? See, okay, if you have to think about it, Uni, I am from PCM. PCM as in, and it's harder for me to understand geography. Just be regular in the class, my dear friend. Don't follow this approach that I have attended first class, then I will attend fourth class, then I will attend eighth class, then I will attend 10th class. If you are regular in the class, trust me, it will be easier. The problem is that you get habituated to such subjects. I leave union executive, still I would understand union legislature, because MPs, MLAs, prime minister, chief minister, defense minister, everybody likes to hear about. Just be regular in the classes. And this is where the subject of geography is different. If you want to go into the depth of it, you will have to pay attention to it. You have to be regular. It will come to you. But if you are impatient that, okay, after 3 classes I have attended it, I have given you that much privilege that I'm attending your class, now you want me to be regular also, then this subject will go away from you. Always it will go away. And heavier plates will always get subducted. Yes. Here it is given slight subduction. If you are reading it light, don't read it light. It is slight. Means little amount of subduction. Eurasian plate, granitic materials, it is made up of it. Yes. Praneeth, why are you not answering my questions? Maybe your questions are so very difficult, Praneeth. It is going beyond my head. That is why. I don't know. But I'm unable to look at your question, my dear friend. That is why I'm unable to answer. There were water in Tethys Sea caused water vapor. Yes. Himalayas are growing up means the plates are moving. Yes. All convergence leads to earthquakes. Yes. Please write in one line in the slide why Himalayas not have volcanoes. Okay. In this case, no volcanic eruption because of two reasons. First reason, not enough molten materials and gases are created. And secondly, presence of very hard and thick rocks crust due to deformation. Okay. Now here, basically, that is what you observe in the case of continental convergence. But see, this is the fold. When we observe the formation of fold mountains, these are how the folds appear to look like. So across the convergent plate boundaries, you'll find the formation of fold mountains, oceanic trenches, you'll find the formation of islands, right? So seamounts, etc. All of these you will find to be created as a landform. Now, in the region around the Pacific, across the entirety of the region of Pacific, there is some or the other convergence continuously going on. For example, in the region of southeastern Pacific, you have South American plate, South American and Nazca. That convergence is going on. In the region here, you will have North American and Pacific plate. That convergence is going on. Then here, you'll find the Eurasian and basically the Pacific plate. That convergence is going on. Eurasian and Pacific plate. That convergence is going on. So various different types of convergences are going on. Here, if you observe, Philippine Sea plate and Pacific plate. Philippine and Pacific plate. Here, if you observe, around the region of Tonga Islands, Pacific and Australian, Indo-Australian rather. So all around the region of Pacific, different types of convergences, they keep on happening around Pacific. So as a result of that, around the entirety of the Pacific. And mind you, Pacific plate is an oceanic plate, right? In the region around here, if you talk about it, even Nazca plate is an oceanic plate. Whenever you have a convergence of an oceanic plate, volcanic eruptions and earthquake is commonality. So in all these convergences, earthquakes and volcanoes are commonality. Earthquakes and volcanoes are frequent, right? So when earthquakes and volcanoes are basically more frequent, entirety of the region around Pacific almost on a regular basis, be it Mount Pinatubo in the region of Philippines, be it Tonga, Hunga Tonga, Hunga Hapai in the region of Tonga, be it Mount Fuji in Japan, be it Mount Shasta Rainier in the region of North America, or Cotopaxi in the region of South America. The entire region around the Pacific frequently experiences earthquakes and volcanoes. This is the region dotted with many oceanic trenches also. That is why this is what is also referred to as Pacific Ring of Fire or the Circum-Pacific Ring of Fire. Okay, this is a favorite area of UPSC. Now, in the sense that UPSC will frequently ask you a question both in the optional portion of geography as well as in general studies portion of geography, that what happens in the Pacific Ring of Fire, or how do you explain the Pacific Ring of Fire? What are the events of Pacific Ring of Fire? What are the characteristics of Pacific Ring of Fire? This question is repeated, has been repeated umpteen number of times by UPSC. So as a candidate, all that you need to write is that in the region of the Pacific Ring of Fire, first of all, what is Pacific Ring of Fire? So the region around the entirety of the margins of the Pacific Ocean, which experiences frequent volcanic activities along with frequent earthquake events also, is famously regarded as the Pacific Ring of Fire. Now, then in the body, you can start writing that the theory of plate tectonics helps us ably explain that why these events unfold. These events unfold because of different types of oceanic convergences which happen across the entirety of the region of Pacific. They can largely be categorized under continental oceanic convergence as well as oceanic convergence. Draw the relevant diagrams for both the types of convergences. Observe and also indicate how these convergences will lead to volcanic eruptions, and give the name of the various plates, and your job is done and you will be able to secure good marks. So that is basically the approach that you need to follow, and that is more than sufficient. Okay, I hope that is understood. How all the around Pacific Ocean convergence takes place, because if convergence takes place at one side, then opposite side it may be lead to divergence. See, North American plate is moving over the region of Pacific Ocean. It is moving at a greater speed. Pacific Ocean is also moving in the westward direction, but North American plate is moving at a greater speed. When you talk about the Pacific Ocean, here it is moving in this direction. Nazca plate is expanding, but the South American plate is colliding with the Nazca plate. Hence convergence on all sides. Okay. Now, after this, okay, how to write conclusion. So conclusion for these type of questions should be very simple and technical also. So in conclusion, you can write here that these convergences not only lead to creation of newer islands and volcanic events in many of the cases, but they are also critical for biodiversity in this region. More needs to be understood about these types of convergences in order to better predict the occurrence of earthquakes and volcanoes, which can impact lot of life and population property, etc. Like that you can conclude. So in these technical questions, generally it is advisable that follow the approach that more needs to be understood. That's it. Okay, we need to research more. If you have a problem based question, for example, water scarcity, we are facing water scarcity, crop failure, in those cases the conclusion has to be a kind of a forward looking, a solution that you have to write. But in these kind of technical questions, always summarize it, that how it impacts life in that region, biodiversity in that region, or why more research needs to be carried out, and so on. Okay, I hope that is understood. Now, here we talk about the Indian plate and its movement. Now, when we talk about the Indian plate and its movement, now this is something which concerns us all, after all, isn't it? So, we are here going to talk about the formation of the Himalayas. But the process of formation of Himalayas is not as straightforward as you would have read in many books, that you had the plates colliding, converging, leading to the formation of Himalayas, etc. No. Himalayas are amongst the younger mountains of the world, amongst the young fold mountains of the world. Their creation has been experienced only around 65 million years back. Their creation has not been forever long, right? Now, even that creation has been spread out, because when we talk about the Himalayas, I hope we are aware that the Himalayas consist of three ranges. The Great Himalayas, or the Himadri, created around 55-60 million years back. The Middle Himalayas, or Himachal, created somewhere around 40 million years back, 35 to 40 million years back. And the newest one, that is the Shivaliks, which have been created around 15 to 20 million years back. Right? Now, here, I want you to understand, notice carefully what happened. And as the famous quotation goes, observe and follow the chronology. Chronology is important here. So, roughly around 200 million years back, if you observe, all the land masses, basically the Gondwana land, what we talk about, that was present very much closer to the region of South Pole. You had Africa, India, Antarctica, South America, Australia, Madagascar. All of them were joined into a large landmass. But somewhere roughly around 150 to 120 million years back, you had significant amount of convection current, which happened all around the region of Antarctica. As a consequence of that, in fact, it was a large landmass. Convection current happened between those land masses. So these land masses, they started separating. They started moving away from each other. All of them, they started moving away from each other. Because observe here, by the way, at this point of time, this portion and this portion were joined. Even Madagascar was very much joined with the portion of western coast of India at that point of time. But nonetheless, they started separating. They started moving northwards. Now, as the Indian plate was moving northwards, here, in between the Indian plate and Eurasian plate, there was a large sea that was named as the Tethys Sea. We are talking close to around 120 million years back. At this point of time, Indian plate was moving at a speed of around 15 to 20 centimeter per year. 15 to 20 centimeter per year, which is very fast. When you consider the plate movement, a speed of 15 to 20 centimeter per year is considered to be very, very fast. Now, obviously, it was aided by various factors. For example, in the southern Indian Ocean, you have the region of Reunion Islands. When Indian plate came over the region of Reunion Islands, there was so much amount of volcanicity there. It's continued for a couple of millions of years. And that further sped up the movement of Indian plate, because now you had more molten materials underneath the Indian plate, which could shoot it up forward. So Indian plate continued to move. It continued to move at a speed of close to around roughly 15 centimeter per year. Now, to the north of it, you had the Tethys Sea, and further to the north, you had the Eurasian landmass. Now think about it and try to imagine this. Here, basically, when you consider this, let's suppose this is the Eurasian plate. This is the pen that you see. Let's suppose it represents the crust of the Tethys Sea. And here comes the Indian plate with a certain amount of force. Now, as the Indian plate was moving forward, It was pushing the Tethys Sea underneath the Eurasian plate. Some portion of Tethys Sea was being consumed by the Indian plate also, right? But the rate of movement was so very high. Indian plate was moving at such a great speed that Tethys Sea could not undergo subduction at the same speed. In the sense, if I simplify it, let's suppose Indian plate is moving at 5 centimeter per year or whatever is the speed, and the Tethys Sea is undergoing subduction underneath the Eurasian plate at 5 centimeter per year, that rate. If both the speed are similar, by the time that the Indian plate would have reached here, Tethys Sea would have been completely subducted. But what if the speed of movement of Indian plate is 15 centimeter per year and the speed of subduction is very less? So in that case, subduction could not be completed and the Indian plate was crushing towards the region of the Eurasian plate. And due to that compression, Tethys Sea floor did not have enough time to undergo subduction. So the Tethyan Sea floor simply was uplifted. In the sense, if you push this further, if you push this further, what will happen after some time? If it cannot undergo subduction anymore, it will be pushed upwards, it will be uplifted. The Tethyan Sea floor was uplifted. And then after that, you had a full-fledged collision between the Indian and the Eurasian landmass. And then the existing fold of the Tethyan seafloor, along with the other materials nearby, they started getting folded to create the mighty Himalayas that the world stands in awe of. Now, how do we know all this? How do we know that the Tethyan seafloor got uplifted? That is based upon the evidence of the fossils. In the region of Himalayas, for example, even in the region around Mount Everest, you'll find the presence of rocks such as limestone. Limestone. Remember what we studied last week. Limestone is formed and created where? Wherever you have had a shallow water body, because limestone deposits are created underwater. So wherever limestone is created means that region would have been underwater at some point of time in the geological history of that region. Then furthermore, upon further studying those Himalayan region, it was found out that the region has got many of these mountains. They have got fossils of marine organisms, organisms of marine origin. So when you have fossils of marine organisms, how come they are present on top of these mountains, on the region around these mountains? Obviously, this region would have remained underwater and has been pushed up. As this convergence still continues, Indian plate is now moving only at a speed of around 1 to 2 centimeter per year, but it is moving nonetheless. It is compressing into the Eurasian landmass nonetheless. As it continues to happen, the height of the Himalayas continues to increase. The height of Mount Everest continues to increase, and the region continues to remain unstable. That is why the region around Uttarakhand, Jammu Kashmir, Himachal, Nepal, Assam, Sikkim, Arunachal, these are the regions, even for that matter, all the way up till Delhi. These are the regions frequented by earthquakes because of this kind of convergence. So that is the entire process of formation of the aspect of Himalayas. Let us try to formulate it, encapsulate it, and then try to move forward. So here, when we talk about it, the process of formation of Himalayas. Of formation of Himalayas. Okay, so here I will give you an idea, a rough idea stage by stage, and you can basically formulate your own encapsulated story with it. You can write your own content based upon those step by step procedure that you have. Can you please use white PPT instead of purple? No, my dear friend, the I think you will have the PPT with white background. That link is also there in the students portal itself. There itself you will find it. But on this platform, we will use the purple background PPT. Okay. Now here, when we talk about it, the first stage, movement of Indian plate. Indian plate. So you had the Indian plate, which had separated from Gondwana land, which was rushing towards the region of the Eurasian plate. And here you had the sea. This is the region of the Tethys Sea. This is your Indian plate, moving at around 15 to 20 centimeter per year. Eurasian plate was moving at a speed of 1 to 2 centimeter per year. This is your Eurasian plate. Now, then subduction of Tethys. So, as this Indian plate is pushing and the Eurasian plate is undergoing that convergence also in both these areas, but because the push by Indian plate was much more, the subduction was happening greatly under the Eurasian landmass. Here also some subduction was happening of the Tethys plate, but greatly underneath the Eurasian landmass. That is where more amount of subduction was happening. Narrowing of the Tethys. Of Tethys. This is your Indian plate. This is your Eurasian plate. Now, because there was significant amount of subduction happening underneath the Eurasian landmass, what it meant was in this area, you had very frequent volcanic eruptions in this area. So few volcanic eruptions on Indian side also, but majority of these volcanic eruptions would happen in the region around the Eurasian plate. That is why in the region around the present day, around the region of Tibet, around the region to the north of it also, to the west of it also, you will find many rocks which are volcanic in origin, which are igneous in character and volcanic in origin. They have been created during this process. Then the third stage. The third stage is the upliftment of the Tethyan seafloor. Upliftment of Tethyan seafloor. Right. Now, why did the Tethyan seafloor get uplifted? I will write the reason of that as well. So here, basically, the speed of movement of the Indian plate was so high. It is estimated, by the way, that roughly close to around 5,000 square kilometer, 5,000 square kilometer of the Tethyan seafloor underwent subduction underneath the Eurasian plate. But still, more could not get subducted because the speed of movement of the Indian plate was very, very high. So, as the speed of movement of Indian plate was very high, the Tethyan floor basically got compressed, got created into folds. You had the upliftment of Tethyan seafloor. Indian plate, Eurasian plate. So here, why? because speed of movement of Indian plate was so high here that entire subduction could not happen, and the seafloor was thrown upwards. Okay, the seafloor was thrown upwards. After this, what happened was basically continental convergence. Continental convergence. So here you had the Indian plate and the Eurasian plate colliding, and including the upfolded portion of the Tethyan Sea floor, you had the formation of the range here of the Himalayas. Nadeem, my dear friend, do one thing, write a mail. You have my mail ID? Write a mail to me. We'll take a look into it. So this is how the fold of the Himalayas got created. But then we do know that the Himalayas have multiple different folds. Himalayas don't have only one fold which is present, isn't it? Himalayas have multiple different folds. So how did that get created? So understand this. When you consider this particular fold, you are talking about thick rocks getting folded into a mountain shape. But this is not a piece of paper which can get folded in any which way that you manage. This fold or the compression and the deformation of the rocks will have its own limit. You cannot deform the rocks endlessly. You cannot end up deforming the rocks such that such kind of a fold can be created, can you? Obviously not. So once that deformation limit is reached, what happens after that? The rocks, they break, right? So that is when here you had formation of the second range of second range of Himalayas. How did that happen? So this stage, eventually, as the convergence continued, by this time the rate of movement of Indian plate had reduced to around 5 centimeter per year, right? So the speed of movement had reduced. Now here after this, you had the rocks could not get deformed anymore. So the rocks actually broke at the zone of convergence itself. Okay, you had the development of a fault or a crack. So this is what we will later study as thrust fault that got created. As the compression continued, the existing mountain continued to grow taller. There was some movement always which would happen at these places. And furthermore, even this area that started getting folded. So you had a creation like this. You had a fold which was created next to it and an existing earlier fold. Right? Now then, furthermore, this process continued. This happened second range of Himalayan formation happened around 35 to 40 million years back. Then furthermore, you had another kind of range, formation of the Shivaliks. So basically, even this process continued, where the height of the second range continued to increase. And after some time here also, the rocks could not get deformed anymore. So the rocks would break from here. So you had the development of another kind of crack, and a third mountain range got created. A third mountain range got created somewhere 10 to 15 million years back. Okay, so you had the three mountain ranges getting created. And this is the reason why in the earlier two ranges, you will find significant evidence of marine deposits and marine fossils also, because they have been created due to the rise of the Tethyan sea floor. Because why? Because the Tethyan sea floor was pushed up, as it could not subduct, because the rate of movement of Indian plate was very, very fast. Once that Tethyan sea floor had been lifted up, then the continental convergence pushed up the rest of the landmass also. Furthermore, that folding continued to happen, the height continued to increase. But the deformation cannot go on endlessly. The rocks here would basically fail under huge amount of stress. That is when they developed a crack. When they developed a crack, then what happened? Further push meant that the existing mountain would grow taller, would grow slightly thinner. There would be some movement here. Another range came up here. Another range came up beyond that. Even today, this movement continues. Even today, as this movement continues, the height of the mountains, the height of the Himalayas continue to increase. And any movement which happens here or here triggers massive earthquake. The earthquake which is triggered in the region around Nepal, Kathmandu, that is a movement happening between these two places. And much more interesting is the fact that we know that these processes have created a crack here as well, beyond the Shivaliks, in the region of the Indo-Gangetic plains. And that is the region where, in the region of Delhi, in the region around northern portion of India, in the region around Assam, you experience very frequent earthquakes. That happens because of movement of crust and rocks across this place. And more importantly, it gives us an idea that in the coming years, there will be a fourth range of Himalayas which will get created. In the region of northern portion of UP, northern portion of Bihar, northern portion of Bengal, Assam, there will be a fourth range of Himalayas which is bound to come up. Okay, but that will be around 5-10 million years away into the future. So that is about the formation of the Himalayas, the process of convergence, and the part of plate tectonics. That is where we'll restrict the discussion here for today. I hope the session was helpful and meaningful to you guys. Okay. Why volcanic eruption in Eurasian plate? Does it because of the Tethys Sea? Subduction of the Tethys Sea, yes. Okay, Rohit, I'll take a look into it. Okay. Through this process, one day total Indian landmass will be destroyed if the convergence continues to happen. But even then, whenever you will have the encountering of the hard rocks of the Peninsular Plateau, it will be a different mechanism altogether. Mount Everest is part of the Himalayan range, yes. Okay. Is Himalayas increased by 5 centimeter every year? No, it varies. It varies. It is not as if it will increase by 5 centimeter only every year. It varies. Okay. You need to draw the diagrams while you write the answer. Yes. Was the Asian continent a part of Laurasia or Gondwana land? Substantial portion of it was the part of Laurasia. But when you consider Arabian Peninsula of it, that is the West Asian portion, India, Southeast Asia, all of these were part of Gondwana land. Okay. So that is where we'll end the session here for today. We will continue from this further tomorrow as we proceed ahead. Okay. So till we meet again tomorrow, do take care of yourself. Thank you. Goodbye.